Hello, good evening, participants. Now the session day 2 going to start within a few minutes. So before going to start the session, I introduce our speaker for the day. Dr. Ratish Kumar Panchatarthi is a professor of civil engineering and dean of planning and development at the National Institute of Technology, Warangal, NITW. He completed his doctorate of engineering in 2006 with the prestigious Japanese government's Mombusha Scholarship and was a postdoctoral fellow under the Japan Society for Promotion of Sciences (JSPS) in 2009 to 2010. He has published 256 technical articles, including 103 SCI journal papers, contributed to 17 book chapters, and authored 4 books. Additionally, he holds 5 patents with 3 more in progress. Dr. Panchatrathi has guided 13 doctoral students, 76 master students, and 42 bachelor students batches. He has been recognized with multiple awards, including the Aftab Mufti Medal and several scholarships from Japan, Denmark, and Italy. He is also a senior member of the Indian National Academy of Engineering and serves as an auditor for the Central Pollution Control Board for fly ash. With 17 years of administrative experience, he has overseen key roles at NIT Warangal, including head of the civil engineering department, and he has been instrumental in large-scale consultancy projects, including the construction of super specialty hospital and a 70 crore bus terminus. Currently, he manages over 450 crores worth of construction works at NIT Warangal. So, I would like to call Dr. Ratish Kumar sir to start the session. It's a pleasure, sir, to have you. Please, you can start the session, sir.
Yep. So thank you very much, Jalal, for a nice introduction.
Welcome, sir.
And I think my screen is visible.
Yeah, visible, sir.
And I'm perfectly audible.
Yeah.
Yeah.
Hello?
Yeah.
Yes,
Yeah,
sir.
I'm audible, isn't it?
Yeah, you go ahead, sir.
Okay. So first of all, thank you very much to the management of Lord's Institute as well as the Department of Civil Engineering, and for giving me this opportunity to share some of my insights into some of the ideas, because the topic itself as the ATAL program itself is something related to, you're saying, sustainability, innovation, trends, etc. So these are some of the keywords which I think I've tried to pick up also in my talk. And basically, that there are several sustainable development goals. I think I've tried to project these goals on the screen over there on the left side, so you can see that. And mostly I'm working in the area of goals 9, 11, 12, and something related to climate also a little bit. So these are some of the goals I'm working with. And you can see that there are several keywords which I'm trying to mention over there. One is performance, which is very, very important, as everybody knows. When I say performance, obviously, people know that I'm talking related to strength as well as durability, right? And then I'm using another keyword, which is life cycle assessment, which is something like, the amount of, the process which goes into making a product, and the amount of energy which is required, basically, also is a part of it. That's like embodied energy. So in this process, what is the amount of, what are the different stages which are involved in this life cycle assessment? I'm also going to touch upon. And contrary to the point that, everybody talks about recycled aggregate concrete, I think we try to go a little bit in a slightly different way, that we try to go for multi-recycled aggregate concrete. I mean, where we thought of, exploring the idea of not only just single recycled, but is it possible to go for generations of recycled also? And before I actually go to the next slide, I would say that you can, any point of time, because I can't see you people, you can, any point of time, you can say that please stop, and then you can ask me questions, because I like more of interaction than only one side. Okay, so you can always say that, please, sir, I have a question, and then
Sir.
Yes.
Hello.
Yes.
Sorry for
Yes.
interruption, sir. Sir, the question answer, because of the huge participant, the question answer will be at the end of the session, sir. Means before going to the end of the session, means it was 15 to 20 minutes. They will put on their queries in chat box. So checking out the chat box, you can convey the queries into the answer.
Yeah, no worries.
Okay,
Right,
thank you very much, sir.
That is
Go
also
ahead,
fine.
sir.
Right. So I'll be talking about these aspects. That means touching upon these 3 important aspects. That means your strength and durability, your life cycle assessment. In fact, I'll be touching upon a different type of what do you call the boundary conditions. In fact, they're cradle to gate, or basically when you talk about recycled aggregate, we go all the way from cradle to the gate and then come to the cradle again. So which is something like a, including the recycling process also. So this is the topic of discussion, and obviously when I talk about life cycle assessment, I'm going to touch upon the embodied carbon dioxide, embodied energy. And when I say performance, I'll touch upon strength and durability. And when I say multi-recycled aggregate concrete, I will also talk about what are the different stages basically which are involved in developing a multi-recycled aggregate, and then its use in concrete, right? So this is what I wish to talk about. Obviously, the main goal is sustainability, right? So that is actually the basic topic and basic thing which you wanted me to talk about. Everybody knows the definition of sustainability. In simple terms, if you want me to tell, it is called as geo or jinedo. That means if everybody understands Hindi, I mean to say that आज के PDB रहना है, कल के PDB रहने लायक बनाना है. So which means that is actually given by the Brundtland's report as development that meet the needs of the present generation, but at the same time without compromising the ability of the future generations to meet their own needs. So that is what is a Brundtland's definition, and obviously comes without any compromise on the ecological health of our planet. That means whatever we are trying to talk about, the resources which you are trying to consume, in this generation, you have to also see that the next generation will have enough number of resources to take care. It is something like a parental heritage, right? That's something like that. Your father gives something to your son or a daughter, and then that heritage is going to continue. Now, let me just try to put here the world population development. You can see that we are moving close to 10 billions, and that's a very big challenge, in fact. And sometime in 2024, we have already defeated China in terms of population, as is very evident here, that we have defeated China. Now we are the #1 leaders in the world in terms of population. We don't call it as population, we call it as human resource. So that is the greatness of our country, and we can see here. And the point here is why I'm trying to mention this is when there is an increase in population, obviously comes with several challenges in the sense that to match the increase in population, we need to think about the growth of how to basically increase infrastructure, right? And to increase an increase in population is also going to result in energy consumption, which is actually one of the very, very important key things which we have to think about. And also we have seen in several of the metropolitan cities, in major cities, we are seeing that there are two things. One is either drought or flood. So that means there is also a water scarcity which is actually is adding to that. So what I just want to say from this particular slide is that there is an increase in population, and all of us, whoever is participating, whoever are your students or whoever are your teachers, everyone, we all have a key role that we have to think about. What are the different ways and means of course, increase in infrastructure is going to be there, but what is it we can do in a sustainable way? Because at one point of time, we used to think in the terms of strength and durability, but now we are thinking in terms of sustainability also. So that's what I mean to say here, right? Now, let me just talk a minute about this carbon footprint. I think we also know something about an Earth Overshoot Day. I don't know if somebody don't know about it. I just let me just put it in a very simple way. That the meaning of Earth Overshoot Day is that day when the resources of the Mother Earth basically are getting consumed in that particular year, right? So that means the Earth is going to produce some resources per year, let us say, and you are trying to consume those resources. And you can see the way we are trying to consume those resources is very, very pathetic. You can see somewhere in 70s, for example, you can see that whatever we are trying to produce for that particular year, we were trying to go straight into December or November or something like that, as you can notice. But when we are trying to go more towards, the present generation or 2024, for example, because 2025 Earth overshoot is not clear, but you can see that it's something like August 1st, we have really reached that overshoot day as far as your 2024 is concerned. That means whatever energy, whatever resources we have tried to produce in the year 2024, for example, is X number, right, which has to go up to the end of the year. We have completed our resources by August 1st, which obviously means that we have consumed. That means your September, October, November, December, we are trying to eat upon the resources which is for the next year. So which obviously is going to, as you can notice that this is basically going down and down, which means it's an alarming thing that we have to think about how to basically enhance our resources, in the sense enhance our, or go in the direction of sustainability, so that we can try to consume our resources more and more towards November, towards December. That should be our attempt, right? So that is the meaning of Earth Overshoot Day. I'm also putting a footprint here on the left side, because these days it's a very common thing that we try to talk in terms of CO2 footprint or carbon footprint, etc. So I thought I will try to put the carbon footprint. And as far as the Indian part is concerned, we are somewhere over there. That's called as a big two part. And though, there are other countries which are actually producing a lot of carbon footprint. When you say China here, when you say Japan here, when you say United States here, when you say Russia here, when you see Germany here, definitely, ours is okay as compared to China as well as US is concerned. Which means actually, when you try to talk in terms of the number of Earths which is consumed, as you can see, this is approximately equal to 1.75 times of Earth, right? And if you see, the amount of energies, or the amount of number of planets, in terms of number of planets, if you try to compare, if you try to expend the resources like how Qatar is expending, you can see it requires 9.3 times of Earth. That means the resources which is produced, for example, one Earth is not sufficient. It is 9.3 times of Earth. As far as US is concerned, it is 5. As far as Russia is concerned, it is 3.3. As far as China is concerned, it is 2.2. Whereas in India, there is a good news that, we are still at around 0.67, as you can notice there. It could be around 0.67, means, 0.69 or something like that. But we are still less than 1 Earth, which is something like a good news, in fact, right? But, at the same time, we cannot be complacent, because, as we are trying to go, as I'm trying to say that, the population is increasing and we have crossed China now, our demand for infrastructure is increasing, our need for resources is increasing. So that is the reason why we cannot be complacent about saying that I'm 0.67 times of Earth, right? Now, all things I'm trying to talk in terms of the global ecological, or the glowing ecological footprint. I'm talking it in that particular sense. Now, if you try to understand also the energy, India's projected demand, why all of us are talking in terms of sustainability, that is a background which we have to really understand. If you try to see the India's projected demand by 2047, right? We are talking in terms of Viksit Bharat. We are 2047. We are trying to achieve, a lot of things by 2047. We have a vision for 2047, and all of us in different directions, whether you are engineers or teachers or working in different areas, we are actually aiming in that particular direction with different vision and mission statements, which we are trying to come in tune with the Viksit Bharat concept of India. Now, if you try to see the energy demand, the global energy demand, or India's projected demand by 2047, the India's projected demand is close to around 18,125 terawatt hours. And I might not be interested much in terms of industry, which is 9,920. But I'm interested more in terms of buildings, which is 2,287 terawatt hours. That is our projected demand by 2047, right? And of course, it definitely involves several things like, the residential heating or domestic lighting or whatever it is, whatever the different appliances which we are trying to use. Together, if I try to compare, our projected demand is 2047. And also, when you're trying to think in terms of, growth in infrastructure, can we live without cement? That's a question. Can we depend totally on geopolymer? That's a question, because there are a lot of things which are still to be explored in geopolymer, which is actually, way back in 1970s, David Otis has started that. But there are still several questions which are there before us, before we totally accept the geopolymer, because there are several issues like, corrosion issues there, leaching issues there, several things are there. So I will not say that we can totally survive without cement at all. And if you try to see what is our demand by 2050, right? In 2020, it was 450 to 600 million tons. With growth in population, with growth in infrastructure, with increase in infrastructure, etc., we are now at the level of 780 to 1360 million tons of cement is required by 2050, right? So that means in 2047, our demand is this much, and very close to that, our matching. If I try to think in terms of cement for increase in infrastructure, it's around 718 to 1300, something like so many million tons is required. The news is not very much better in case of China also. China is also having the same type of, and in fact, you can see that it's around 2.2, right? 2.2 times of Earth, in fact. So I will say from that point of view that India is still doing better, and with all you budding researchers and you teachers, etc., who have been working in the direction of different methods, ways, and means of reducing the carbon footprint, which we are trying to do. We can't at this point in time. We are trying to go with completely leave away with cement and try to go for alternate materials, and I know that we are all doing that. And there is a lot of improvement which we have made, in fact, as far as the research is concerned. But the question is, how much amount of this is actually going onto the ground? So that is again an important thing to be thought about. Now, at the same time, our Prime Minister Modi ji has actually made 5 tall promises in COP, Confederation of Parties 26, which was conducted in Dundee, in Scotland, where we have made, as far as that's a responsibility on each of us, basically, which we call it as, in fact, Panchamrit. We call it as Panchamrit. So there are 5 promises which we have made to the world that we are going to realize these things. One of the important things is, we are actually dependent upon the fossil fuels. So we want to raise the non-fossil fuel based energy capacity. That's one very, very important thing. That's that actually one of the important things which I'm also going to cover in the the idea of life cycle assessment is also to touch upon a little bit about what are the different fossil fuels we are trying to use and can we really reduce them. And that too, we want to raise the non-fossil fuel based energy by 500 gigawatts by 2030. That's a challenge, right? That's a tall challenge. The other thing is we want to basically reduce the country's energy requirements, through renewable energy resources. We mean to say solar energy or, hydel power, or for example, all these renewable energy resources, we want to basically go wind energy or whatever it is. So we want to basically improve ourselves by 50% and by the end of 2030. And then we want to basically reduce the total carbon emission also by 1 billion tons between, probably in 2024 as well as 2030. We want to reduce the total projected carbon emissions by 1 billion ton. When I said carbon emissions are to be decreased, obviously we have to really think about reduction in the carbon dioxide or cement also, because normally it is said that 1 ton of cement is going to produce around 0.89 or 0.9 tons of CO2. So which obviously means that some people say 1 ton and 1 ton of CO2, it's around 0.89, 0.9 tons basically. And we want to basically reduce that, and we have to think about ways and means of doing that. The next thing is, the fourth promise what we have made is we want to make reduce the carbon intensity by 45% by 2030. That's another challenge. And then finally, we are trying to make the fifth promise. We made the fifth promise that our country is going to become net zero emission by 2070, right? And this actually we can achieve this only when each of your individual campuses or each of your individual spaces where we are trying to do will actually contribute to that. So that's a very important thing. So I want to just say that these are 1, 2, 3, 4, 5 promises which we have made from our country to the world, and obviously that responsibility we have to shoulder. And then these 5 promises are called as Panchamrit, and this we have made in COP 26, Confederation of Parties 26 meeting, which is a global meeting basically which has taken place in Dundee in Scotland, right? So that's what is the challenge now. So all of us are really equally responsible to achieve these 5 points. Not just the Prime Minister has made a promise and then we are going to forget about that. All of us have this responsibility. Now let me try to slowly enter into the concrete part and then slowly go into the performance part, etc. I will not be going too much deep because I also will touch upon the multi-recycled aggregate part. But if we try to see, at one point of time when you think about the heritage structures, for example, we were actually a part of this Ramappa World Heritage Site. In fact, we did a lot of work in the area of collecting the material from the Ramappa site where the bricks in the Santam Santorum area basically were broken, and then the mortar which was basically used for connecting the bricks, we tried to collect the mortar. And then we did a lot of sampling basically, and then we could crack a recipe for this 815 years old temple, So we could try to crack the recipe, which was using different types of organic additives, several things which they were trying to make, and use of lime basically, which is actually a well-established thing. And the technology which was used in that particular building is basically, or heritage structure is basically a sandbox technology, where the sand will be confined between the the wall, different confined, and then your structure will be placed on that. And obviously it has been suffering, taking good amount of quakes, and then it's passive in nature, and at the same time the issue of water striking up, and not much of a problem is there with respect to lime. Right now, when it comes to the question of concrete and reinforced concrete, so bacha hai, you can see it's only 1850, 1867, and around 1900 or so, your reinforced concrete has come into picture, right? And that means we do have a traditionally established concept, which is lime. And there is good breathability. There is what you call, these days we are talking a very fancy term, which is called as carbon dioxide sequestration, right? And lime has been doing this carbon dioxide sequestration basically, and developing calcium carbonate, which is indirectly developing a good amount of strength, in fact, right? And if you see, if you try to go down the line, you can see that in 1920s, Christus concrete, the recycled aggregate has come in 1945, is a self-compacting concrete, ultra high performance concrete. These days we are talking about roller compacting concrete. These days we are trying to talk about, what do you call, yeah, the fibrous concretes, or everything we are trying to talk about. And these are all, which has started only in these years. And then, the people started thinking about, at one point of time, the concept was durability is already normally achieved through strength. But then we started realizing that it's not the question of achieving durability through strength, but it is basically a performance-based design, not a prescriptive type of design, where we thought that, the strength is achieved through durability, not durability through strength. And then slowly, we have been moving in the direction of sustainability. And then we have been thinking about these three important points. That is, we talk about strength, we talk about durability, and then we entered into another domain, which is called as sustainability. So that's the reason why all the time we are now talking in terms of sustainable transportation, sustainable water resources. I mean, what do you call it? The sustainable, and in terms of environment, in terms of technology, in terms of, what should I say, social aspect, in terms of economical aspect. So there are basically, when you talk in terms of sustainability, there are four important things. One is called a social aspect, environmental aspect, economical aspect, and the fourth one is technology. In fact, technology was basically looked at in the environmental aspect. Now we try to make it as a quadruple bottom line approach instead of a triple bottom line approach. And we have been slowly moving towards sustainability, and that's the reason why all of us have been talking in terms of, whether it is FDPs or whether it is research, etc. We've been talking in terms of sustainable concrete, sustainable mortars, etc. Now, let me talk about the recycled aggregate. Of course, it's not whatever I'm trying to talk about. Recycled aggregate is not new. I told already that when I'm trying to build up the, what you call, the path towards sustainability, I was trying to show that, in 1940s, 1945, 50s, around that particular time, the concept of recycled aggregate has started. And then we started thinking about that the resources are basically dwindling. Our infrastructure growth is there. We need a lot of infrastructure growth, because to match our population, we need to increase the infrastructure. And to match infrastructure, we need to go for a lot of construction. And when we have to match with the construction, obviously we depend upon the materials which are available. We have natural resources like sand, for example, like aggregate, etc., where slowly they are basically dwindling down. And then we have been working on alternates to cement also. And I'm sure that everybody is working something or the other, like either binary or ternary or tertiary type of materials in the form of either rice as cash or GGBS or metakaolin or ground grounded blast furnace slag, or anything like that. We are trying to talk about different types of bioashes, biochars, etc. So these days we have been talking about a lot of different types of materials. But they stuck a point here that when you're trying to talk about concrete, more than 60 to 70%, approximately 60 to 65 to 67% is being occupied with aggregate. So while I'm trying to concentrate on the 33% part of replacing with cement, etc., cement, etc., why not we concentrate a little bit more on the 67 percentage of the total amount of concrete which is aggregate? And is it not really good to also concentrate by in the direction of going for alternates to aggregate also. That's the reason why some of you or many of you might be working in the direction of alternates to aggregate also. People are working on RoboSand, people are working on CMOB these days, coal mine overburden, for example. We are trying to replace your coal mine overburden as a can it be a sand material replacement for sand? And then of course your crushing crushed dust and waste sand, granite powder, and whatnot we are trying to basically use as a replacement for sand. And ceramic waste, glass waste, different types of waste we have been using. In case of we are trying to basically, even fly ash is coarser type of fly ash, or what should I say, bottom ash, for example, is also being used. Can it be used as a replacement for sand also? So we are trying to think about ways and means of basically replacing the what you call aggregates also. Even the same thing in case of coarse aggregates, we are trying to go for reclaimed asphalt pavements. We are trying to use glass. We are trying to use PET bottles. We are trying to use rubber waste, etc. Which obviously means that the concentration is also there on a bigger, a big brother role in case of concrete, which is one of the major constituents. Basically, 67% is occupied by the aggregate. So this is that particular concept basically. And one of the important things where we are trying to use the replacement is also in terms of construction demolition waste. So this is one thing which is which people have been doing that, but unfortunately, there should be a lot of pickup in this particular direction, because India is recycling only 1% of the construction demolition waste. And although if people remember that there is a Ministry of Environment and Forest as well as the CND rules are there, where we very clearly say that we have to mandatorily replace the demolition waste up to 20% in any of the construction. But the problem is implementation. The problem is only with implementation. At one point of time, we have been working a lot in the direction of fly ash. And if you try to compare people who are just little bit, doing research in the area, a little bit of a decade or decade and a half or so, that, when we were trying to do the work on fly ash and other supplementary cementitious materials, when you try to compare the cost of PPC as well as OPC, for example, right? Now, these days we are talking about Portland Pozzolana cement. We're talking about Portland slag cement. We're in fact talking about also the replacement. Like why should we go for only what do you call the cement-based limestone? Why can't we go for medium-grade limestone? And then we are talking about limestone-based cement, and we are trying to use different types of cements like Portland slag cement, etc. At one point of time, if people remember, if you try to compare the cost difference between the ordinary Portland cement versus the Portland slag cement, the Portland slag cement was less. Nowadays, we are not really finding ordinary Portland cement at all, which means yeah. Somebody wants to talk? Okay. So, am I audible, please? Can I just get a reply from your side that I'm audible?
Yes, sir, you are audible, sir. Go ahead.
No, I thought somebody is asking a question. Okay, right. So I'm perfectly audible. Okay.
Yeah.
So, this is what was the situation at one point of time. But slowly, now we have realized that Portland Pozzolana cement, Portland slag cement, limestone-based cement, we have been doing a lot of research in that particular direction. We, I mean, all of us, right? We have been doing a lot of research, and we try to accept that there are different types of admixtures in the form of supplementary cementitious materials, which we have been trying to mix, left and right. In fact, that's again a very big thing, that whatever supplementary cementitious material you get, you try to add in cement without actually knowing what is a life cycle inventory. Is it really going to help me in decreasing the import energy? Is it really going to help me in decreasing the carbon footprint? We are not thinking. Left and right, we have been using the different types of materials, which is in fact, I will call it as a crime if you don't know properly. Right. So that is where is one area where unfortunately the life cycle inventory is not very popular. Life cycle assessment is not very popular as far as our countries, our context is concerned. And we are trying to basically depend on the resources which are there from other countries basically. And only except a very few people are working in the area of life cycle inventory and life cycle assessment, in fact. So the point here is that, if you want to go towards to realize the goals of sustainability, it's very important that you also try to take the big brother role in the form of modifying the aggregates. And your construction demolition waste is one thing. IS 383, which is actually the code for gradation of the aggregate, it has very clearly given that if you want to go for 25%, you can try to replace in plain concrete, 20% in reinforced concrete. And if you want to go for a lean concrete like M15 grade concrete or 15 MPa concrete, you can even go for 100% replacement. The only question is, unless and until we try to disseminate and then we try to publish, people will not be getting that confidence. The other thing is about the supplementary materials also. If people remember, if all of you remember that, nowadays, the IS 10262 has come up with the mixed proportion, which is including the supplementary cementitious materials, which means really there is now a confidence that we can try to use the supplementary cementitious materials in the mixed designs, right? Similarly, when IS 383 says that you can use 25% and 20%, in fact, we have been using 50% also. In fact, for M30, M40 grades of concrete, in fact, we can try to use that. So now, when we are trying to disseminate our research like this, then people start accepting that, TK, we can try to use recycled aggregate also. And that is the reason why we made one step forward also in the direction of what we call it as multi-recycled aggregate concrete, where I know that, first generation recycled aggregate is there. Can I try to crush this first generation, go to the second generation, third generation? Because nowadays we are trying to think about makeshift structures which are temporary type of structures. So obviously at the end of 10 years or 15 years, we're demolishing and then reconstructing. So that's why I thought that, can we go for different generations also? Which means if the structure is surviving for 60 years, and if you're trying to think about makeshift and temporary structures of 10 years, can I go for 3 generations of aggregate, recycle, and then what is the benefit I'm going to get versus what is the amount of carbon dioxide footprint I can try to reduce? These are some of the things which were there in my mind. So we try to bring up this particular concept, right? Now, if you try to see the sustainable use of materials, obviously, as you try to go towards the, what do you call, the route always will be that you have to use a matching aggregate quality. You can try to get the matching aggregate, the concrete grade, which is actually a good sustainable practice, rather than use the aggregate also left and right. And if you try to go for utilization of the recycled aggregate, there are several benefits. As I told you that, I'll try to put it broadly in the sense of social aspect, economical aspect, environmental aspect, and technological aspect. So technologically, when I'm trying to replace, I'm able to get a certain level of grade of concrete. Economically, obviously, I'm reducing the dwindling resources, obviously. So, I'm really not trying to mine it so much. And the third thing is, from a point of view of environment point of view, when I'm not using the resources, when I'm not trying to really, excavate and explode and excavate the resources, obviously I'm trying to put a check on the, the environmental aspect also. And obviously I'm also trying to concentrate on the social acceptability, because, for that social acceptability, it really requires a good amount of research and dissemination. So that is what is the idea which I'm trying to take here. Now, we did some research in the laboratory. It's not that, whatever research we are trying to do, it's only in the laboratory scale. We try to basically go into a slightly higher level to try to go into an industry scale also, where we try to basically produce some what are called as your, precast blocks, or for example, in case of the paver blocks, etc. We have also tried to develop using a third generation recycled aggregate also. It's not that whatever research, please remember, all of your researchers, teachers, so please remember that our research should never be restricted to the laboratory. And don't think that, something add kar diya, usme ek paper aa gaya, uska, your, you have developed written a paper, and then by adding certain, these days we think about microstructure characterization, etc. And then develop a good paper, publish a paper, gone. That's not the point here. The point is, now we are trying to go from publishing to patenting to industry scale. That means whatever I'm trying to do in the laboratory, is it going to an industry or not? Otherwise, our research is definitely going to go as a waste. This is what is my feeling. Now, as far as the research on this particular direction, but of course, it requires a good amount of basic studies to be done in the laboratory. So in our laboratory, we try to take a conventional concrete, crush it in the jaw crusher, get this first generation recycled aggregate, make a second generation recycled aggregate, crush it once again, make a third generation recycled aggregate, and then with that you develop a recycled aggregate concrete. And we try to basically study the strength point of view, the durability point of view, and then we try to understand that when I'm trying to do the crushing part, I'm really expending a good amount of energy. So am I really trying to, the energy versus the amount of economy which I'm trying to get, the energy versus the carbon footprint which I'm going to decrease should also be calibrated. That's what we try to do basically in case of 3 generations of recycling. Now here I just want to put one point here, because of the paucity of time, I really cannot go deeper into that. But I only suggest that, because the aggregate is occupying a bigger role, 60-70% of the part is aggregate, you can definitely try to reduce the paste content. If I can try to basically pack these aggregates in such a way that the amount of paste content can reduce. From that point of view, I mean to say that when the paste content is basically decreasing, obviously the cement content is also going to decrease. So the point here is that when I'm trying to concentrate more on the aggregate part, I also would like to bring it to your notice that there is something like a particle packing theory. In fact, there are different methods out there. We have monodisperse system, polydisperse system. We have a discrete approach where we try to go for binary, ternary models, etc. We have a continuous approach where we have the what you call the different methods like modified Anderson, Fuller and Thompson, etc. These are the methods which are there. Some of the basic concepts, I think people who are really interested in research can also work in the direction of using the modified Topher model, JD Diwar model, and the compressible packing model. So these are the three models which are very popular as far as the discrete approach is concerned. And modified Anderson model is a popular approach as far as the continuous approach is concerned. I'm not really going deeper into this. People can refer. And if in case you have any doubts, you can just put particle packing theories and Ratish Kumar, you can get some papers you can go through. And you can also, ping in any doubts, etc. If there are, you can try to do that. The concept is only something like achieving maximum density by packing these aggregates in such a way that you can get the minimum amount of space to be filled up with the cement paste. Of course, satisfying the minimum cement content, right, requirement. That is also there. Now, the reason, which has actually propped up in our mind is because we have this IS 383, I think, table 5, where we have the different, the seal sizes. And as you can notice that there is a large gap in 4020, 2010 directly and 10.4.75. So we thought that is it really possible to fill up? Of course, one of the important things I would also like to put up is when I try to go for crushing plants, I should also give a model to them because it should be whatever I try to do should be a practicable thing also. So when I try to do the crushing part, it should be in such a way that it generates different particle sizes. And if I try to add them, try to mix them up in a certain fashion of, 50% of this, 40% of this, or 10% of this, or 30% of this, 20% of this, 10% of this, 5% of this, like this, if I try to add, in what way, what is the best way of basically adding up the bigger particles, smaller particles by considering what are called as different, the wall effects, for example, the container effects, for example, the compacting effort, for example. These are some of the important aspects which are really finely tuned into these, the mixed, the particle packing theories, wherein I can get a particulate system in such a way that the density is going to be very good with a lesser number of voids, which are really accommodating the cement paste or the paste phase, meaning that the cement paste can also be, the cement content can be decreased, meaning that I'm trying to also lower the carbon footprint indirectly. So please try to understand this particular method. Because of the paucity of time, I can't go deep into that, but I can only say that there are three methods which are very popular: modified Taufer model, JD Diwar model, and compressible packing model, which was originally proposed by D. Lalard. So the concept is basically maximizing the density of the particles, reducing the paste content, right? Now, if I try to just give you some idea about this is the loosening effect. These are the wall effect where the bigger particles are fitting into the smaller particles, or the smaller particles are fitting into the bigger particles. We get a wall effect as well as loosening effect. And when you try to basically fill it up, this is what I'm trying to say here, that if I try to compare a standard method versus a particle packing method, if you can notice my ticks on the red ticks on the left and right side, you can notice that the volume which is filled with aggregate basically is slightly increasing. And then I'm trying to leave lesser amount of paste, right? Additional paste is there. And then you can see the volume of voids is basically decreasing. So that means I'm packing in such a way that I'm trying to arrange so that more amount of aggregate particles are there with satisfying the minimum cement content, of course. In fact, I can try to reduce the cement content, total cement content per se, but I can definitely try to get a very good packing also at the same time. Meaning that with the same cement content as what is recommended, I can get a higher grade of concrete or higher strength in the concrete. That's what is the meaning. Now, if you try to see how it basically goes, I'm not going for different generations in this particular case. I'm trying to show natural concrete aggregate, which is conventional concrete, and this is recycled aggregate 1. When I try to talk about the particle packing approach or something like that, you can see that I'm trying to show you different things: modified Topher, JD Diwar, and compressible packing model. versus the IS 383, which is a traditional the codal provision. In fact, based on the CPM model, what we worked out, we are also proposing that the code can actually modify the table 5 if it's possible, right? So you can see that this is how we basically try to do it. We have a 20 to 12.5, we have 12.5 to 10, and we have 10 to 4.75, and then we get a what do you call a combination of different values, right? 20% of this one, 60% of this one, and something like 20 to 28% of this one. And then there is a certain point where there is an intersection, which actually is a point where you get the maximum density or maximum packing you are going to approach. That's called as maximum density or maximum packing or particle packing. So the same thing, as you can notice in I'm trying to show in case of recycled aggregate also, the same approach is adopted, and then you do the gradation based upon the different sizes of the aggregates, and then you try to arrive at what percentage of passing through 10 4.75, passing the 12.5 and passing the 20 to 12.5 can be taken as an example. I'm trying to tell you, wherein you can try to take each of these different percentages to get a packing in such a way that there is very less room for the voids to be there. That is what is called as the concept of particle packing approach. Now here I'm just trying to show a table. I know you will not be very much interested to see the tables, but I have to also show some figures, right? Some standard values basically. Now, if I can try to show you that there are different methods which I just now proposed, and if I may show you the CPM model, which is, for example, the natural aggregate based concrete here versus the first generation, the second generation, and the third generation, you can see that with a lesser amount of percentage variation, I could get using the CPM method, a good amount of density, though I'm also able to get with the JD Diwar model and the modified Taufer model. If I try to use all other different advantage which I'm trying to get. Sometimes I go with the JD Diwar model or the compressible packing model or the modified Taufer model, but all of them are equally good. And I try to compare with the IS 383 versus the ASTM code versus the Euro code, and you can see that there is the difference between what you're trying to get is basically good. I mean, when I'm trying to do in case of these particle packing methods versus the IS 383, etc., there is definitely there's an advantage with respect to these particle theories. So that's what I just want to say. Now, let me try to see there is one disadvantage or one serious problem in case of recycled aggregate, and more so in case of multi-recycled aggregate, because as you can see that the paste content or the old mortar, which we call it as adhered mortar, is basically going to be increasing in case of as the generations of recycled is increasing. And obviously, when you try to basically do the jaw crushing, which I just proposed earlier, obviously the adhered mortar will be removed, and there are certain other methods also which I just try to make a mention of. That we have the thermomechanical treatment or mechanical treatment or simple soaking method or acid treatment. These are some of the methods which are actually there, so we can also try to do them. But of course, whatever method I try to use, I definitely have to show that it is economical, it's not energy consuming also. So we have to think about that. So everything we have to, in fact, try to compare. And I have also come across once I try to pack properly, then I try to estimate what is a binder intensity index, and I can calculate the binder index as what is the quantity of the binder versus what is the compressor strength. And you've noticed that as the binder intensity index is basically going in the right side, and you can see that there's a drop in the compressor strength, and that is actually depending upon the type of method which I'm trying to follow. So the advantage I'm trying to get in case of your compressor, the packing theories versus the IS 10262 part is concerned, right? So mind you that there are two important things which I'm definitely aware of. Number one is the water absorption is definitely going to be more in case of aggregates, recycled aggregates, and for which there are different methods where we can try to do that. We can either try to compensate for that water absorption, or we can basically try to soak it in water and then wait until it is coming to a saturated surface dry condition, and then try to make the concrete. Because the interstitial transition zone, the interfacial transition zone, which is in between the aggregate as well as the paste phase, obviously there's an interfacial transition zone in between, which is a weak phase, and that is more so because you're going to get multiple number of interfacial transition zones as you are trying to go towards the different generations of recycled aggregate. So I'm aware of that. I mean, we know that, and we are trying to basically trying to go for a subtle level of crushing, so that much amount of embodied energy is also not going into that. So all that I'm aware, all that is taken into account. Now, these are some of the surface treatment methods. And as you can notice, one of the methods which I'm trying to talk about is water soaking, which can, to some extent, it can be effective. And then we can try to go for abrasion and then try to get a certain amount of, removal of the old water which is there. I think it's better if you go to thermomechanical treatment type of method where you try to do the oven drying and then go for abrasion. And then there's another method which is still more better, that is called as acid treatment. But when you try to go for acid treatment, what is it I'm also trying to do with the aggregate, and how much amount of the treatment has to be done, and how much amount of what you call damage I'm trying to do the aggregate is also one thing which I have to talk about. I think we can settle down with the thermomechanical treatment, which is okay, or we can basically try to go for modifying. In case of first generation, for example, we can try to go for compensating the additional amount of water absorption, and we can try to go for saturated, bringing it to surface, saturated surface dry condition. But you can accept normally from the literature, you see that around 20 to 24, 25, 27% of old mortar which is there, which is adhered onto the mortar, onto the aggregate, it is still able to develop around 30 MPa, 25 to 30 MPa concrete. So that's not a great problem as long as I'm trying to remove up to 25% or so. I think it's still there, 25% is still there. That's not a great problem. So that's what is the point here. Now, let me try to also give some figures as far as the compressive strength, split tensile strength, flexural strength are concerned. I think I'm trying to show here the 7-day strength, the 28-day strength there. This is from the IS code method. This is a CPM method. This is again, when I'm trying to compare the different grades of concrete, I'm trying to show in the 4 figures what you're observing over there, the light blue one, the orange one, the green one, and the violet one. They are basically corresponding to the conventional concrete, the first generation, the second generation, and third generation. So we could try to get a good benefit in terms of the CPM model, because you can see that there's an increase in the strength which means that with a lesser amount of cement I can still get the targeted compressive strength, so which is definitely something good. And I could get the same thing in case of 50 MPa concrete also, like 30 MPa concrete, and I could do the same thing with respect to the split tensile strength and also with respect to the flexural strength. That means by modifying the inferior type of aggregate, even if it is second generation, third generation also, I'm trying to get a benefit provided I'm using a right particle packing approach. So that is what is the point here I want to make a mention here. Now, going to when I say performance, obviously there is another thing which is called the durability. When I say durability, I'm actually what we did is we tried to take some 4 different chemical species, right? Which is HCl, H2SO4, NaCl, as well as a magnesium sulfate. That means your sulfate attack is considered, chloride attack is considered, the acid attack is considered. And when I'm trying to subject the specimens to different species like this, I try to calculate 4 different parameters, in fact. So they are nothing but one I called it as acid attacking factor, where when I try to soak these, put these specimens in, let us say, different types of species like HCl, H2SO4, NaCl, MgSO4. What is basically the change in the dimensional stability, like the dimension of the structure, which is called as the acid attacking factor. And then, there is a loss of mass which is going to take place, which I call it as acid mass loss factor. And there is a loss of strength which is also going to take place at the end of 7-day, 28-day, when I'm trying to basically soak these specimens in the different species which I've mentioned. Obviously, there's going to be a loss in the strength also. So when I try to combine these 3, that is acid attacking factor, which is a dimensional factor, acid mass loss factor, which is a change in mass, and acid strength loss factor, which is basically a change in strength, I try to combine all these 3 things by made a unified factor, which is called as acid durability loss factor, which is the durability loss factor, which I'm trying to mention here, which is nothing but durability loss factor is equal to mass loss factor multiplied by strength loss factor multiplied by attacking factor. So when I try to combine these 3 things, I'm trying to get what is called as durability loss factor. And I try to determine this with respect to the conventional concrete, first generation concrete, second generation concrete, and third generation concrete, which you can see these are the corresponding specimens which I try to make. And they are exposed to NaCl, MgSO4, HCl, and H2SO4. And I could get this parameter from a mechanical point of view, that loss of strength, loss of mass, loss of stability, dimensional stability. And I could come up with one unified factor, which is called as durability loss factor. At the same time, what I also did is, from a what I call non-contact type of method we try to use, wherein I can actually, is it possible to basically, a technique which is called as digital image correlation. So this is something like a digital image processing, where we basically try to, is it possible that I can try to take an image of the sample when it is not subjected to any type of chemical attack or chemical species? And once it is subjected to a set of chemical species, if I try to take the image, is it possible to understand the changes in the color stability? And then can I try to make out that, okay, this is subject to a good amount of loss, and probably this could be because of this particular reason, etc. And I could make what do you call a good number of samples in the laboratory, hundreds of samples we try to make, and then we try to store it as a database, which means that, this is something like a non-contact type of understanding the change in the color or the color stability of the element when it is subjected to different types of chemical species. Of course, we try to use a method which is called as image software, and then we try to basically capture the images before and after subjecting it to these chemical species at the end of different curing periods. And then we try to come out with what are the different changes which are going to take place in terms of the surface texture, in terms of the what I call the color change also. And we try to basically classify like this. If it's HCl, you're seeing orange shade. H2SO4, you're seeing white precipitate. NaCl, white precipitate, of course, could be accompanied with certain amount of efflorescence, etc. And NgSO4, white and dark gray patches. So when I'm trying to basically record these values for hundreds of specimens, I have a database, which means I just try to use what is basically required is only something like a DSLR camera. I want something like a color checker, and I require a certain amount of luminescence to be maintained. I require a certain amount of temperature to be maintained. I keep on taking the images of these pictures at the end of different levels of curing. Curing in the sense, after curing, subjected to different type of chemical species, as I'm trying to show there. And then I can obviously try to understand the surface porosity. I can understand what are the changes in the colors because of the attack. I can understand that if it is subjected to a very good amount of acid attack, the entire surface gets peeled off, and only the the aggregates are going to project. And when I try to take the image of that, obviously the intensity is going to be more. So intensity in the sense, intensity of light is going to be more. From this, I can basically try to make out that, okay, this is subjected to these types of things. And it's not just a simple data. We have made hundreds of specimens and then recorded a data, so that when I go to the site, for example, this can actually serve as a precursor. I don't say that this is the only thing which is going to decide that this is subject to this type of attack, but this can definitely serve as a precursor. This can definitely serve as something like a quick reconnaissance inspection. I can try to go take a photograph on this structure, and then I can basically try to compare that color, and then I can probably try to come to some conclusion so that I can further go for investigation in that particular direction. That's what is the point here. So this is what actually you can see that I'm trying to put a color checker over there, and I'm trying to take the specimen, and I'm trying to use a lux meter basically to maintain a certain amount of luminescence, right? It's around 110, 120, something like that. And then what is basically you have is a DSLR camera, and then it's a high resolution DSLR camera. I take the images, I try to compare with the color checker, say that this is the color, and then I try to subject it to different specimens, species, chemical species, and then different generations, as well as I try to get different parameters here. The parameters could be, it could be a simple RGB, or it could be something like LAB, it could be something like XYZ, or it could be something like hue, saturation, as well as intensity. In fact, hue, saturation, intensity is very, very close to the human eye, which actually human eye can sometimes we try to. It's difficult to basically recognize a different color in some cases, but that HSI is going to be more better from that point of view. LAB is actually going to be better where you want to compare the curing methods, basically, right? So there are different methods which are there in the images software. We try to pick up some of them, and then we try to make a good amount of images, and that data is there, which I can use it to compare on the field. Yeah, this is again to show that this is an RGB data which I'm basically collecting. And then this is basically the color stability analysis, which once I know the RGB values, that is red, green, blue, of course, which are on the different vertices, as you can notice over there. And if, for example, there is a contamination, color contamination is going to be there with white mixing in that, obviously I'm going to get different other types of colors, which is basically the pure color is basically considered to be hue. And if there is any amount of contamination, we call it as saturation. It's saturated with other colors. And if you have an intensity, as I just now told, the intensity is going to be more if, for example, the top surface is completely abraded away, and then you have only the exposure of aggregates. Obviously the intensity is going to be more because it emanates good amount of light. So the brightness of the color is again this thing. So when I try to calculate this HSI in terms of mathematical form by using the RGB, how do you get RGB? Basically I'm trying to compare with the color checker, and then I have some values, and using the images software I can get these RGB values exactly, and then I can calculate the HSI values, and I can try to compare these HSI values when it is not subjected to any attack, chemical attack, or versus the chemical attack. So that's what we try to do here, and you can see that for different types of grades. Here I'm trying to show a 30 MPa concrete as well as 50 MPa concrete, and this 30 MPa concrete I've tried to restrict now to only design using IS method as well as the CPM method, and I could get the corresponding chemical exposure to HCl, H2SO4, NaCl as well as MgSO4, because these are some of the important. You can ask me why are you going for these things? The chloride attack as well as carbonation, for example, are very serious as far as the corrosion is concerned. And as you know, more than 40% of the structures get damaged because of the chloride attack. And sulfate attack, it can be intrinsic, it can be extrinsic also. Please remember, it is intrinsic, when you try to basically make a concrete which is already having a good amount of chloride content, which is more than the acceptable value. It could be extrinsic, where your structure is in the proximity of a chloride environment. Similarly, for example, the sulfate attack, there could be, inert aggregates could be there. Normally, we say that inert aggregate, that a couple of times we do encounter what you call the reactive type of aggregates, or for example, the soil on which your structure is existing could also be leading to a sulfate attack on the structure. So that is the reason why very close to matching, and there could be an acid attack, which is very, very dangerous. The passive layer which is there on the steel basically gets removed because of this acid attack. And obviously, it creates a path for the other chemicals also to enter inside. And so it becomes a cascading effect when the porosity gets lost, as well as, one of the things, for example, the carbonation is more, for example, then obviously, your alkalinity of the concrete is going to get down and come down. And then obviously, because of the acidic atmosphere, the surface process, what you call the passive layer, which is normally there on the steel, it gets removed. And obviously, the attack from other chemicals are also going to take place. That's the reason why the chemical species which you have selected are basically corresponding to that which can really cause a serious effect on concrete, right? And we can see some very good data. You can see the H value is basically the highest for the sulfuric acid exposure, and then it is the highest for the third generation recycled aggregate, and it's the lowest for NaCl as well as MgSO4. And then it's the lowest for concrete design using CPM method, which obviously means that the the mixes which are basically designed using the compressible packing model are more dense, and they could really result in lesser amount of the external attack, right? And similarly, if you try to see the saturation also, it is the same, highest in case of HCl, and it's the lowest in case of NaCl as well as MgSO4, right? And then when you also see the intensity, it's definitely the highest in case of HCl as well as H2SO4. And it's something like a reddish gray precipitate is actually forming, and the intensity is obviously going to more because it is subjected to an acid attack. And obviously these values are also a little more as compared to the HS in case of NaCl as well as MgSO4 also. And it is the highest, obviously, in case of third generation, right? And definitely the samples, as you can notice from the figures here, that the samples which are designed using CPM method are performing much better when compared to the samples which are done by using your IS code method, right? Right. Now, once the XYZ, once the RGB are calculated, the XYZ value, this is again a different color space where we can basically quantify, right? And CILAB is another color space. There are 4 color spaces which we try to explore. One is RGB, the other is XYZ, the other is CILAB, and the other is basically your HSI. So these are the 4 different types of color spaces, which actually, if you are really going a little deeper into the image analysis, images software, if you try to use, you can basically try to get a good idea, and you can see the vertices are basically red, blue, green, and when they get contaminated, obviously they are going to be the different types of colors, and whether you're moving close to green or red or orange, that is actually compared with the original specimen, which you are original beam or a girder on the site versus the data which you are trying to preserve in your laboratory. That's a standard database. You try to compare and then say that ye gum hai, ye jada hai, which means obviously this is exposed to this type of atmosphere, right? That is basically the concept of image analysis. And then obviously the last thing is basically the LAB, which is best in case where you are trying to go for different types of curing, right? Coming to the last aspect, that is the third aspect, which we call it as the life cycle impact. I try to talk about the sustainability in terms of performance, that is your durability as well as your the strength initially. And when I say durability, I was talking in terms of mechanical durability. And then I slowly went into the image analysis, where I tried to say that this is one best way, one easy way, basically, where you can try to get a good amount of guess about what could be the, what you call the exposure to which this particular structure has taken place, whether it is subjected to acid attack or chloride attack or sulfate attack, or what sort of exposure. It could give me a basic idea from where basically I can try to go a little bit further, and then explore a little deeper, and then using some other non-destructive techniques, because this is what is called as an invasive technique, where we are not really touching this sample on the site. We are trying to take the images and then trying to compare with the ones which we are there which are there in the laboratory. Now, going to the third part, which is actually called as a life cycle impact assessment. In fact, normally when we try to calculate do the life cycle impact assessment, we try to form a certain goal and scope definition. In fact, this sort of life cycle impact assessment I can do for cement, I can do for fine aggregate, I can do for coarse aggregate, or meaning that, you know, I can actually try to develop when I'm trying to develop a product in the form of a paste or a mortar, or for example a concrete per se. It's going to involve different types of constraints, and for these constraints I can always calculate what is the life cycle inventory of each one of them, and then I can calculate the total amount of embodied energy which is required, what is the amount of energy which is required to make a product, which is called as embodied energy. And in the process of developing this particular product, what is the total amount of carbon dioxide emissions? Is it really good to go for developing this product? Because in the process of basically decreasing CO2 content, at least I have to get some advantage of reducing the carbon footprint if I want to go for a new material, or if I want to go for replacement of a certain material, if I want to think of a novel material like what we are doing these days, for example, you know, biochars or bioashes, or, you know, different types of concrete we are trying to develop, different types of supplementary cement, LC3, for example. We are trying to do all these things basically to achieve, you know, lessening the carbon footprint, and, you know, with lesser amount of embodied energy, I want to develop a product, right? That's what is the point. And in this, we have something like a life cycle inventory, which is important. Unfortunately, not many people are working in this particular direction. This is a gray area. Somebody can actually go into this particular direction. If you really want to work in a new one material, or if you want to go for a binary, ternary, tertiary combinations of different materials, it's good that you try to establish a life cycle inventory of that material. Otherwise, we don't know whether it is doing good to the concrete or bad to the concrete. So that's one thing. And then you basically try to establish a life cycle impact assessment. You go up and down basically to check whether I can replace this material, I can increase the silica fume, decrease fly ash, increase metakaolin, decrease this one, add bioash, even if it is 2 to 5% of biochar, which is obtained from a pyrolysis process. What is it doing good for the concrete or the material which I'm trying to develop? And then we interpret the data and then come to a conclusion. In fact, there are different parameters which we are going to examine, like the global warming potential, you know, different types of, I will try to come to that particular thing. So here you can see that when it is coming to the question of impact assessment of the multi-recycled aggregate concrete, I'm trying to think about all the different steps, which are raw material procurement is one thing. When I say raw material procurement, I'm thinking in terms of cement procurement, fine aggregate procurement, coarse aggregate procurement, and then the transport. And when I'm trying to basically make these aggregates, how much amount of diesel is basically used, because I'm going to crush it from a bigger material to a smaller material. I'm going to transport this material to the gate. That's what is called as, there are different boundary conditions. In fact, when I'm trying to develop the product, there's life cycle models. In fact, there are different types of boundary conditions. We call different, the popular 3 boundary conditions are cradle to cradle, cradle to gate, or cradle to grave, right? And then we also have different other type of boundary conditions also, cradle to, you know, end of gate, or cradle to grave, like this. So different types of boundary conditions are there. But in case where you are trying to go for recycled, you are coming from this source and then you are again going back. So which means it is something like cradle to, once again you are coming to the cradle. That means you are taking a whole circle here in case of recycling of the aggregates. So you are having this level, and then you are trying to manufacture the concrete. When you are trying to manufacture the concrete, Obviously, there is going to be mixing, there is going to be transporting, there's going to be placing, there's going to be curing. All these things are there. And then after that, you are going to use the product. You're developing a product in the form of bridges or buildings or anything like that. And then you are trying to basically use for some time, you're crushing it and then you're demolishing. And then you are developing the aggregate once again. And that aggregate basically you are trying to use as a raw material once again here. So that's what is a full life cycle we are trying to use when you are trying to go for cradle to cradle, right? So this is one of the boundary conditions which we try to work out and which is true in case of multi-recycled aggregate concrete, right? So this is basically trying to use the material again and again, which means I'm really not expending the rare earth resources which are obviously there. That means I'm indirectly trying to reduce the carbon footprint. Indirectly, I'm trying to concentrate more towards what is called as your the entire life cycle part, etc. Okay, so which means I'm also trying to concentrate on how basically to make the resources to be more useful beyond this August. That means that's what a very simple way to tell it, right? Now let me try to bring you some data with respect to a 30 MPa concrete. This is what is the data which is actually calculated as far as the input is concerned, and this is the output basically. When I say output, obviously I'm thinking in terms of emissions, right? So that's what is an important thing. So if you see the materials, of course, there are argillaceous materials, calcareous materials, you have the rotary kiln as far as the cement is concerned. And then, there is a good amount of, I was trying to talk in the first two slides about the fossil fuels. So there's a lot of fossil fuels which you are trying to use, right? You can see petroleum, lubricating oil, pulverized lignite, etc. All these things are the different types of fossil fuels which we are trying to use basically. And then this is the corresponding inventory we try to calculate. And then these are the different components are there, and these are the emissions. I'm not going to talk the like 12.11, 16.18, something like that, but please go through this. These are the different materials which are going as an input for making the cement. I'm talking about cement here. This is the inventory which we have calculated for each of the materials. Remember that this is not an easy task to basically calculate, because we try to collect this data from the different cement manufacturing industries from the south side, north side, east side, west side, and middle part of the country where the cement is being produced. And then we came to a conclusion about the inventory, depending upon where. In fact, I'm trying to only show one such inventories, but we try to do the inventory for different materials, because somebody is producing a multi-recycled aggregate in south or north or west, for example. I should actually be in a position to calculate that inventory according to that particular cement which is available locally, because it is not expected that you try to transport the cement from one end of the country to the other end of the country, because that's going to again expend a huge amount of resources basically in terms of transport or diesel or something like that. So that is one thing. So these are the corresponding emissions. I have done similar exercise in case of fine aggregate also, as you can notice here. And then this is the inventory. These are the components. Basically, in case of sand, what we have is diesel burn in the building machine, right? And then we have something like electricity, which is going to be there for making the sand. So that's what is the total amount of the total amount of emissions which are calculated like this. And basically, as everybody knows that the important thing in this particular case is the transportation, which is definitely going to consume a good amount of diesel. And obviously, to crush, you also require electricity. So that is the reason why electricity and diesel consumption are the major emissions. Obviously, they are going to emit carbon dioxide. So they are the major emissions as far as sand is concerned. Similarly, in case of coarse aggregate, obviously, coarse aggregate also needs crushing of the border. So basically, you also need to explode. So in that particular case, blasting is required. So whatever are the different types of inventory which is required for that, say diesel, electricity, explosives, oil, etc., everything is calculated even in this particular case also. What I'm trying to show here is basically an M30 grade concrete concept only. And I'm also trying to consider what are the different emissions, and I'm very clear about the SOx and NOx and the CO2 which is basically generated out of this particular process, which is developing the coarse aggregate here. Then what I did is I tried to basically combine all of them. I tried to calculate the total amount of carbon dioxide emissions. I try to also calculate the embodied energy. Embodied energy, I again remind you that it is the amount of energy which is required to develop a certain product, right? And so I try to take the cement here, fine aggregate here, coarse aggregate here, and I'll be requiring chemical admixture also, which is something which is important, right? Now, these days, when I'm trying to reduce the water cement ratio, I can't really pump, I can't really do carry the concrete by trainee pipes, etc. So obviously the chemical admixture is required. Your concrete mixer operation is there. Your transportation part is there, concrete transportation, right? And you also have the water, of course, a little bit, involved in that, which is also contributing a little bit into the emission because in process. And then we tried to do by both the methods actually, as you can notice here. This is the traditional IS 10262 method, and this is a compressible packing model where the total amount of carbon dioxide emission basically for M30 grade of concrete for that amount of cement, coarse aggregate, fine aggregate. You can see the amount of cement basically, and then the total amount of materials when you try to see right from the cradle to what do you call developing the complete 30 MPa concrete. For first generation, this is second generation, this is third generation. This is the conventional concrete as far as the carbon dioxide emissions are concerned. You can see this is a figure. Each time I'm definitely very clear that even in case of third generation also I'm getting certain advantage when I'm trying to design by doing particle packing theory as against the total the traditional IS method. The same is the case in terms of embodied energy also. As you can notice that for the conventional concrete, for first generation, second generation, third generation, as you can notice that definitely these values as compared to your IS method of design, when I try to go for particle packing theory, obviously the amount of energy which is expended to develop the same product, which is 30 MPa concrete, is definitely less. That means the contributions in terms of carbon dioxide is reducing. And mind you, I'm just talking about a certain level of cement, a certain level of fine aggregate and coarse aggregate. And if I try to scale it to an industry scale, you try to imagine how much amount of benefit I'm going to get if I try to simply modify my gradation of the aggregate per se by using the particle packing theory concept. Okay, and in the process of this life cycle impact assessment, we try to basically calculate the different types of the parameters to justify. That is the ADP, for example, the adiabatic depletion potential, which is important. We have this global warming potential, which is also important. Your ozone depletion potential is important, and the acidification potential is important. Of course, all of the things are also important, but they are of the smaller scale. But as far as the impact assessment is concerned, these are the 7 criteria which are basically used to judge how effective your the method is. Right, you can see here that this is the model graph which is using the Open LCA software. We can do by SEMA Pro also, but the Open LCA software is what I'm trying to present there. And you can see that this part is the the input part. This is the admixture and everything. And then this is basically one of the things I'm trying to show you is the adiabatic potential here. As likewise, you can notice that the acidification potential, the adiabatic potential, I'm trying to put on the all the different sides of the curve over there, as you can notice that. And you can see that when I'm trying to show here, you can notice here that the red one what you're seeing outside is basically the conventional concrete, and as you go towards inside, you can notice that when the same thing, if I'm trying to design using CPM, basically it's inside as compared to the outside one. And when I'm trying to go towards CR1, that is first generation, CR2, that is second generation, and CR3, that is third generation, obviously when I see this radar plot, it's very clear that the total amount of the criteria which I'm trying to compare, all these criteria, obviously they are decreasing as compared to the conventional concrete, which is basically on the outer side. I hope you are appreciating this particular thing, that on the outside, we traditionally have the conventional concrete, and on the inside, basically, we have something like the designing the same thing by using CPM model. But inside that, you should notice and you should appreciate here that when I'm trying to go for recycling, I'm getting a beneficial thing in terms of all these parameters, and they are inside the radar plot. You can see here, these are the areas, whereas the conventional concrete is over there, which obviously means that I'm definitely getting a good amount of benefit from the impact assessment point of view. This is the impact values. If you are interested to see the impact values, as you can notice that this is the adiabatic when depletion potential. You can see acidification potential. You can see the the eutrophication potential, and you can also see the global warming potential, which are basically important. I try to compare them with respect to this the graphs here in terms of the amount of decrease, and you can see that the ADP basically it's decreasing by 75-80%, in fact. And as far as the acidification potential is concerned, in case of cement, you can see the significant amount of decrease you can notice there. And same is the case in case of what you call the transportation, as well as the is also concerned, as you can notice. In case of other different types of criteria, it's not just only the four, there are seven different types I'm trying to compare, where I'm also trying to take the human, what I call the toxicity, human toxicity, or ozone depletion potential, or I'm also considering the photochemical oxidation. So these are the three things which I'm trying to compare, and I'm trying to make a comparison over there. This is the contribution percentage as far as the materials is concerned. As you can notice that when you try to come to the what I call the cement part, as you can see with respect to the global warming potential, obviously it's going to be a bigger role, but I can definitely try to decrease if I can try to decrease the total amount of cement content. And so the contribution of cement definitely is going to uh, come down in terms of the all these different types of potential materials. And that is true in case of the first generation, sorry, normal concrete as well as the first generation concrete. Definitely, I'm getting that advantage. In terms of ADP also, I can see in terms of all the materials, there is definitely a drop in the value. And in terms of the acidification potential also, I could see definitely that there is a drop in the value, which obviously means that in terms of all the different criteria, that is the 7 different criteria which I'm trying to talk about, definitely there is a good amount of benefit I'm trying to get. Yeah, I think more or less I will try to come to the end of this, and this is the last slide I want to present. I just want to also give the what do you call the listeners, as well as the budding engineers, as well as the researchers, certain challenges which I'm trying to give you, the way forward I'm trying to give you. Let me talk very briefly about these things. One of the things is, you are trying to basically talk more in terms of developing the material, but as I said, four things are important: the social aspect, social acceptability, economical viability, environmental feasibility, and technologically what I call plausibility. These are the four things which definitely you have to consider. So whoever is working in the different types of materials, please try to think about whether I'm trying to really talking about these four aspects, which we normally call it as a quadruple bottom line approach as far as the sustainability is concerned. Number one. Number two is the standardization and regulation. So this is very, very important, that our research should not go and die at the laboratory level. So it's obviously it should go to a standardization level, where we have to think about thinking about formulating regulations where people can definitely use it. See, there's no point in working so much and then people stop using it. So the implementability is possible only when the professionals or the regulatory bodies are basically bringing this research basically into a sort of a standard. So that's very, very important. So we have to work in that particular direction. The other thing is the long-term performance and durability. Now, there are different types of materials which are, in terms of short-term gains, they are there in terms of strength, in terms of durability, but there are still a lot of doubts with respect to different types of materials, as I also told, in terms like geopolymer, where the fluorescence, the corrosion, etc., is still a problem. So it's very important because it's a very young material, I will say, in the sense that though it was done in 1970s, but these days we are trying to replace with fly ash and GGBS. Of course, is there. We are also trying to go for the other materials which can also go into geopolymerization, right? We have one part and two parts geopolymer. A lot of research is still going on, but it's very important to think in the lines of durability, which is basically to ensure a longevity of the structure. The other thing is, it's very important that these days we just don't try to limit ourselves to just only the materials research, but it's also important to integrate using the machine learning as well as the AI process, where we also think bring in certain amount of what I call monitoring thing, estimate the serviceability of the structure, etc. That is actually an important aspect. The next thing is the environmental impact assessment, I think, which is something like what I'm trying to talk about in terms of inventory as well as sustainability. The other thing is, these days we are actually talking a lot in terms of material characterization. So we can also try to go for micromechanical studies, etc. That's also one more area where people can actually go into, where we can actually combine with the experimental characterization with respect to micromechanical characterization. And then the other thing is also in terms of standardization and certification. So these are some of the things which are just coming to my mind, basically as an extension of what can actually go in this particular direction of research. I'm not really going into the supplementary cementitious materials part, etc., because many people might have talked about that. But I'm more concentrating towards a big brother role, which the aggregates are going to take care in case of your in the sense that it occupies a good amount of space in the concrete constraints. So this is in general about my part on what I can contribute in the direction of performance, life cycle assessment, as well as the sustainability aspect from coming from the in case of multi-recycled aggregate concrete. So thank you very much. And should you have any questions, please, you can just.
Thank you, sir. Thank you very much for your wonderful session. Hope participants will have some queries. Participants, you can ask your queries through chat box so that sir will clarify your doubts.
There's a good number of people actually. There are 284 people. So that's a good number in fact. Good. I appreciate you people for gathering a good number of people, but I would appreciate if I get some good number of questions because I have another 10 minutes of time. So if I can get some good number of questions, I'll be happy. Yep.
Yes, sir. So chat box have been started, sir, for queries. Guys, you are having 10 minutes left, so you can ask questions here in chat box.
Yeah, go ahead. Somebody wants to ask about a non-related topic. Please go ahead. No worries. Padmaja. Go ahead. You can unmute and ask now. Can we check the long-time behavior of recycled aggregate? 100% we can check. And in fact, the way which I try to present in the form of checking through chemical species is something like an accelerated way of testing. You can definitely go for long-term testing also. Long-term performance you can check. In fact, we try to go for 120 days. And there are some specimens which are still lying for 365 days. We are also going to check for that long-term performance. We try to use these specimens basically, in case of pavements also, along with geopolymers, etc. Yeah. Yeah. Somebody is saying that nice and very effective. I have used rice straw in my concrete at 10%. Sunita Sarangi, let me just see that. At 10%, what is the question? At 10% replacement of the ash, the compressed strength decreased lower than. Yeah. See, the straw or fiber is not supposed to increase the strength actually. The strength in terms of flexural strength and tensile strength is going to increase fibers. You don't expect an increase in the compressive strength per se. There could be a marginal increase, but you don't expect the increase in compressive strength when you use fibrous materials. It's not meant for that. Percentage of biochar as a SCM. Yeah, you can use biochar. In fact, you can try to use agro and non-agro based biochars. Somebody is working in the area of fecal sludge biochar also in our case. So we can definitely use that. And then I think to the order of 2 to 5%, depending upon peanut husk or peanut biochar or bamboo biochar or different types of biochar, etc. You can use from 2 to 5% as a replacement for cement. It has a better benefit. Can you suggest me about LC3 cement and can I use in my? Yeah, sure. LC3, as far as the LC3 is concerned, yes, you try to basically. I would appreciate if somebody can actually pick up the clay from the local source, calcine it by yourself, and then use it in LC3. That would be a good thing. Otherwise, LC3 with the which the IIT Delhi have actually patented it and they're supplying it. But I would say that it's very good if somebody can pick up the local clay and then try to calcine it and check the benefits of that. Yeah. Go ahead. Somebody can mute and unmute and ask also. I'm just checking in the chat box if there are any other questions. How much percentage? Yeah, 2 to 5%. I said no. I've used Portland cement with locally available calcine clay and limestone, sir, but I couldn't get the results. You can try with geopolymer, but how much amount of Portland cement you have used with calcined available calcined clay? So you have calcined it. You have calcined develop the clay by what you call burning it up to what you call the muffle furnace up to 800 to 900 degrees centigrade and got the calcined clay. I use Portland cement also, so I don't know, but limestone calcined clay should give, and you can also try in what you call geopolymer also. In fact, that's another research area we can think about. Is there any software or tool used for LCA? Yeah, you can think about Open LCA. You can think about Sima Pro. A rotary kiln calcined clay now. Okay, what is this rotary kiln calcined clay? What is rotary kiln calcined clay? Not sure about it. What type of innovative materials used in rigid pavements? Innovative materials. We can work on rubber-based wrap pre-paved asphalt pavements. You can try to use plastic waste in the pavements. You can actually work on all these different aspects. You can make geopolymer roads. Yep. So I will send you my mail ID also, so that you know I'm putting in the chat box, so that in case you would like to send some messages, because some people are shy in asking questions. So in that case, yep, that is my mail ID. Calcined clay is available in flash calcined clay and rotary kiln calcined clay. Okay, but maybe you can try with the calcined clay by heating it in the muffle furnace and then try to do that. And before that, you try to also check what is XRF, do the XRF analysis for that. What is the oxide composition of that calcined clay? And if you can send me, I will tell you, I'll suggest you what basically is the you can use. Yeah, I would also like to just inform that there is a PhD advertisement has come. In fact, few positions might be there for PhD role in NIT Warangal in civil engineering department also. If somebody wants to register for PhD, you can see the website. Okay. I will also send my number so that you can just call me after 7:30 or so in the evening, because as a dean, I'll be a little bit busy, but this is my number. Can I use GGPS for the paver blocks for the replacement of cement? Yes, certainly you can use. If somebody can use bottom ash, for example, fly ash, for example, that's fine. GGPS, of course, is to be used. Otherwise, you don't get that calcium oxide part is not there. The problem with fly ash is that it is basically amorphous in nature, so you don't get any reactivity, unlike in case of GGPS, which is more what I call amorphous, because fly ash is more crystalline in nature. So without using GGBS at all, you can't get a good amount of requisite amount of strength. So GGBS is required for the paver blocks, because at least you require 20 MPa strength also. Is waste glass powdered the potential to mix with? Yes, it is having a potential. In fact, you do use GGBS. Sorry, you use the what do you call the glass fiber also. You can try to use, because that's going to improve. You can try to go for multifunctional type of fiber concrete also. At the micro level, you can try to modify by using glass powder. Yes.
Dr. D. Annapur.
Yeah, what are the materials used for high performance concrete? Yes. Yeah, different types of materials are there. You can try to go for nano-based materials, nano alumina, nano silica, a combination of nano and micro materials. So high performance of concrete rises cash used in pavements. Yeah, because with pavements normally you require 40 MPa concrete. But still, if the situation demands that you want to use still higher concrete, then obviously when I say performance, you're talking in terms of strength and durability. I know that. So you can use rice as cash also. Yes. Yeah. Shobha, she has raised a hand. You want to speak something? You want to ask something? Okay. Please ask questions, because we hardly meet. So if there is anything which you people want me to suggest or something, I can definitely do that.
Hello, thank you very much, sir,
Yeah.
for the wonderful session. So hope the participants got clarified with their doubts, and even though if you have any doubts, you can go through the chat box as well and the mail ID. After the whole sessions, we'll provide in WhatsApp group the whole presentation and as well as your doubts again. So and thank you very much, sir, for your wonderful session. Now it's time for second session, sir.
Time for
Next session, next
next
session.
session. So
Yeah.
then I'll take the permission to log out.
Yes, yes, sir.
So thank you very much for giving me the opportunity again, and all the best to you people. Right.
Hello, participants. Now the session will start. Before going to start the session, I'd like to introduce the Dr. Annapurna is an assistant. Sorry, Dr. Annapurna is an assistant professor in the Department of Civil Engineering at Osmania University, Hyderabad. With over 3 years of teaching experience, she holds an ME in Structural Engineering from Osmania University in the year of 2003 and a BTech in Civil Engineering from G. Pullareddy Engineering College, Kurnool, both with the first class distinction. Ma'am has worked at several reputed institutions, including VNR, Vinyan Jyoti Institute of Technology, and Sri Vishweswara Institute of Technology, and has industry experience as a CAD and GIS engineer at RM Software India Limited. Her research interests focus on structural engineering, particularly post-tension structures. Annapurna has taught subjects like engineering mechanics, structural analysis, and structural design at both UG and PG levels. She is a proficient in engineering software such as AutoCAD and StatPro. In addition to her teaching role, she contributes to institutional administration, managing attendance marks and timetables. She is dedicated to continuous learning, attending various workshops and training programs. Now, uh, I would like to call ma'am, Dr. Annapurna ma'am, to start the session here.
Yeah.
Ma'am, I'm audible to you?
Yeah.
Yes, ma'am,
Thank
go
you very
ahead.
much. Thank you very much for giving introduction about me.
Yeah,
Now
sir.
I'll
Sir, ma'am.
start the session. Okay.
Yeah, ma'am, go ahead.
Yeah. Is my screen visible?
Yes, ma'am.
Yeah. Good evening, all the participants. Today I am going to discuss about the sustainable construction materials to prepare no cement concrete. So the presentation outline will be, first I am going to tell why not cement concrete. Now we know that cement concrete is more popularly used material. Why not cement concrete? Why at all? Again, we need to go for no cement concrete. Then what is no cement concrete? It is also termed as geopolymer concrete. Then what is the chemistry of geopolymer concrete? Then what are the different sustainable materials available to participate in the chemical reaction in the geopolymer concrete? Then I am going to discuss about some case studies or experimental works conducted in our college. So here we know that OPC is a predominant inorganic binder for several decades, and also the rapid urbanization together with increased industrial activity has resulted in necessity for huge infrastructure development. Because of that, the natural resources are exploited, such as lime, sand, soil, rock, etc., to meet its ever-increasing demand, thus meeting towards environmental hazard and threat to mankind. So, and again, one more very important aspect is manufacturing of this OPC is leading towards a major source of anthropogenic carbon dioxide emission and energy consumption. And also, OPC shrinkage is very high. That is one of the drawback of ordinary Portland cement, and its resistance to aggressive chemicals is also less. And the OPC binder is costly. And in the last very important aspect is in the last decade, we could see that the production of ordinary Portland cement is depletion. That is, it is decreasing because of this sustainable cementitious materials usage is more in the construction. That is the reason thereby promoting this silica alumina rich materials like Portland pozzolana cement, Portland slag cements are most widely used. There is again one more very important aspect is, let us say if we talk about Portland slag cement, Portland pozzolana cement, These materials are rich in silica and alumina. At the same time, it has its own properties. But anyways, if you just look at the ordinary Portland cement, its usage is very wide, starting from the very small constructions to the large constructions. Ordinary Portland cement can be used. So there is a possibility, that means there is a need of replacement of this ordinary Portland cement based concrete with the alternative material, that is alternative concrete. There need the production of no cement concrete. It is also called as geopolymer concrete. So this geopolymer concrete is introduced by Professor Davidovitz. It is nothing but it is prepared using an alkaline liquid to react within a source material of geological origin or byproduct materials such as fly ash, etc. So here silica, alumina rich solids, when they are reacting with the high alkaline solution, it is going to give a geopolymer product. So silica and alumina rich solids will be like pozzolanic materials in the form of fly ash, GGBS, metacholine, etc. And high alkaline solution. Alkali materials like sodium based materials or potassium based materials can be used as an alkaline solution or can be mixed to get the alkaline solution. Geopolymer concrete consists of three types of materials. First is source material, alkaline liquid, and aggregates. Source material, it should be rich in silica and alumina. So it should have a rich amount of silica and alumina. For example, fly ash, GGBA, silica fume, metacholine, ricer's cash, etc. All these materials are rich in silica and alumina, so it can be considered as a source material in the production of geopolymer concrete. In the geopolymer concrete, the source material is also called as precursor. So then this precursor is added with the alkaline liquid. So to have a reaction, interreaction in the source material, some alkaline medium should be there. So that alkaline medium is created with the sodium based material or potassium based material, like sodium hydroxide, which is having high alkaline in nature, and it is added with the sodium silicate to get the alkaline liquid, or potassium based material like potassium hydroxide, potassium silicates are also added to get the alkaline liquid. So these material, when are added to the aggregates, then geopolymer concrete will be prepared. So this is about the introduction of geopolymer concrete. So here, because it is alternative material to the conventional concrete, we need to understand chemistry of geopolymer concrete. Like how ordinary Portland cement chemistry is OPC added with water, it is going to give calcium silicate hydrate gel, CH plus heat of hydration, like that. Here also, how the geopolymer concrete will have a reaction. Geopolymer reactions are chemical reactions involved in the geopolymer concrete. Here we will try to look at now geopolymerization. Geopolymerization, it is a chemical process that transforms aluminosilicate materials into inorganic polymer structures under alkaline condition. So this aluminosilicate materials like fly ash, GGBase, etc., they will be converting into inorganic polymeric structures. And that too, this reaction will occur, or this transformation will occur only under the alkaline conditions. Because of that reason only, the alkaline activator is added. So here in the chemical reaction, geopolymerization process chemical reaction, some stages will be involved. First stage will be the dissolution of aluminosilicate source. Second will be oligomerization and polymerization. Third will be gel formation. Fourth one will be the hardening and crystallization. First, dissolution of aluminosilicate source. Under this alkaline conditions, the aluminosilicate precursors, I said fly ash, GGBS, which are rich in alumina silicate, they will be dissolving under the alkaline solution and releasing silicate and aluminate phases. So this is alkali silicate material, which is a precursor. Under this alkaline medium, it is going to dissolve and it is going to give two products like silicates and aluminates. Further, the silicate and aluminate will have an interreaction. So this is going to occur in dissolution process. After dissolution, oligomerization and polymerization do occur. In the oligomerization process, the dissolved silica and alumina species form oligomeric species, which then react to form a three-dimensional structure. Three-dimensional aluminosilicate framework. If you look at the silica and alumina, When they are again reacting in the presence of this this alkali solution, they will be giving a three-dimensional structure: silica, oxygen, aluminate, silica, oxygen, silicate. So this is this oligomerization, that is three-dimensional structure formation. These oligomers further polymerize, forming a rigid three-dimensional geopolymer network. Let us say this silica, oxygen, aluminate. Again, it will have a polymerization process and it is going to give a three-dimensional geopolymer network. So this structural organization, the final structure of the geopolymer, it is composed of an amorphous to semi-crystalline network with repeating units like silica, oxygen, alumina, oxygen. So in terms of repeating structures, the final structure will be formed. Then the gel formation. So after this polymerization, then the gel formation do occur. So as polymerization progresses, a geopolymer gel are formed, typically consisting of an amorphous to semi-crystalline aluminosilicate network. Now it is converting into semi-crystalline aluminosilicate network. The general formula of geopolymer, if you look at, it is the general formula where M stands for alkali metal ion. Maybe sodium-based alkali activator if you use, or potassium-based alkali activator if you use, it is alkali metal ion. And N will be representing the degree of polymerization, how much degree of polymerization is occurred in that. And Z stands for silica by alumina ratio, which play a very important role in the geopolymerization. Silica by alumina ratio, if it is in between 1.5 to 2, then the geopolymer product will be produced. And this W represents the water content, how much amount of water content is there in the in this particular gel, geopolymer gel. Geopolymerization product will be represented like this. Then after the gel formation, then the gel will be hardened and crystallization. Over the time, the geopolymer gel continues to harden, forming a strong, durable material. Some crystalline phase may form under specific conditions. Let us say, if you look at the simplified version of geopolymer reaction, it can be expressed as alkali, aluminate, silicate. Okay, and again they are reacting and they are giving the three-dimensional structure, which is oligomer, silica, oxygen, aluminate, and the gel phase, then the bound water. So here the overall reaction, if at all, if we just take a typical sodium-based geopolymer reaction, which is specified by the earlier literature, that is using the source material as metakaolin. Metakaolin, that is alumina and silicate, when it is reacting with sodium hydroxide and sodium silicate. So here alkaline liquid is prepared using sodium hydroxide and sodium silicate. When this reaction do occur, then it is going to give a geopolymer product of the form. So this NaSH. So NaSH gel is the final geopolymer product which is going to be produced when the source material is rich in silica and alumina. So that is the reason it is also called as NaSH gel. NaSH gel, that is NaSH gel, is the geopolymer product which is producing amorphous to semi-crystalline geopolymer matrix with strong binding properties. So this NaSH will have strong binding properties and it is going to give strength property to concrete. So this NaSH gel is going to form when silica by alumina ratio in the geopolymer, formed geopolymer will be in between 1.5 to 2. Again, this formation depends on the temperature, curing temperature, because fly ash, if at all, if we make use of fly ash as the binding material, fly ash reactive rate will be very slow. To improve the reaction rate, curing temperature will be increased. And the type of method of preparation, etc., depending upon that, the final properties will vary. Slightly, it will vary. So like this, the geopolymerization process will occur. First, it is all the precursors are going to be dissolved in the mix in the presence of this alkaline medium. Then comes to the next stage will be oligomerization and polymerization. After that, gel will be formed and the gel will be hardened and it will form a crystalline product. If we take silica and alumina rich materials as the precursors, then the resulting product will be NaSH gel. This is the, in brief, geopolymer reaction or geopolymerization process. Then what are the different materials can be used as precursors or source materials in the geopolymer concrete? So here I have given the list of sustainable materials which can be used as source materials or precursors. From starting from fly ash, then comes to GGBS, then silica fume, then rice husk ash, sugarcane bagasse, then marble dust, red mud, metakaolin, limestone powder, alkofene, like that. I have given the list of all the materials, possible materials. I have just taken the list and I'm just showing here. Then how can we make use of this material as precursors? Because to call as a precursor or source material, the material should be rich in silica and alumina. So let us check the chemical composition of each material, chemical composition of precursors. So this is the chemical composition of all the materials starting from fly ash. Fly ash has silica and alumina content 50 to 60%, aluminate will be 20 to 30%, then the calcium will be 5 to 10%. Then GGBS is will be rich in calcium oxide 40 to 50%, then the silica and alumina content. Silica fume, if you take, it has a very high amount of silica content, mostly more than 90%. Rice husk ash will be more than 80% of silica oxide it will have, and the sugarcane bagasse ash, it has 60 to 70% of silica oxide and alumina and iron oxide, because it is this rice husk ash and bagasse ash both are agri waste products. Nowadays, so much amount of research is being done in this particular areas to make use of supplementary cementitious materials in the preparation of concrete. So there is a scope to include even in the geopolymer concrete with the help of these materials. Then comes marble dust. Marble dust also can be used as this precursor or source material because it is having a high amount of calcium oxide. So marble dust compared with respect to GGBS, marble dust cost will be less. If at all, if you are going to have a combination of silica, alumina and calcium oxide, then we can try this marble dust combination with the sugarcane bagasse as rice husk ash, etc. to prepare geopolymer concrete, alternative geopolymer concrete. Then the metakaolin. If you look at the metakaolin, here if we see the literature of geopolymer concrete, the early literature reveals that much amount of work is done, or the initial geopolymer concrete preparation is done using metakaolin only, because metakaolin is proved to be the best source material to prepare geopolymer concrete because it is equally rich in silica and alumina. If you look at around 50 to 55% will be silica content, alumina will be 40 to 45%. So it is proved to be the best source material. So the initial research work is progressed in this particular material, but being the cost of this metakaolin is high, so that is the reason again the research is switched towards making use of the cheap materials like fly ash, etc. Then limestone powder, it is also rich in calcium oxide. It also can be used as an admixture in the geopolymer concrete. Then alkofene is nothing but it is a fine powdered form or modified version of the GGBS. Very, very fine grinded GGBS is alkofene. Alkofene has similar to GGBS, it has calcium, rich in calcium, silica and alumina. Then the cement kiln dust has rich source of calcium oxide. At the same time, silica and alumina also there. And then phosphogypsum, it is again 30 to 35%, like that palm oil fuel ash. Ceramic waste powder, it is rich in silica and alumina. Then ceramic waste glass powder, it is also rich in silica. At the same time, the calcium content will be less than 10%. Then paper sludge ash, it is also rich source of calcium oxide. Then sewage sludge ash, this is rich in silica and alumina. It has a good content of silica and alumina. And the granite powder, then the coal bottom ash, it is also rich in silica and alumina. Then wollastonite has rich amount of calcium oxide and also silica. So like that, all these materials are having silica, aluminate, and calcium oxide. Some of the materials are rich in calcium oxide and some of the materials are rich in silica and aluminate. So there is a potentiality of using these materials or combination of the materials to prepare geopolymer concrete. So one should understand the chemistry of geopolymer concrete to use alternative sustainable materials. Because if you look at the research is progressed, I said first it is started with the metaculling, then it is switched to fly ash. Now in India, most of the studies are done using fly ash and GGBS. So GGBS again, the cost of GGBS is also high compared with respect to the other materials like marble dust, other materials. So that can be added as an admixture to the geopolymer concrete and we can prepare a sustainable, more sustainable geopolymer concrete. So with that intention, I have just shown all the possible materials along with the chemical compositions. So after looking at all the geopolymerization process or chemistry of geopolymer concrete and the materials, source materials, now we'll switch to how the source materials are produced. What is the source? Fly ash, it is actually produced from the combustion of coal from the thermal power stations. So this from the thermal power stations, here we'll get two kind of ashes. Ash, that is, one is bottom ash, other one is fly ash. Bottom ash is coarser in size than fly ash and the reactivity will be less than fly ash. So the fly ash is the one which is captured from the flue gases using electrostatic precipitator. This fly ash will be rich in silica and alumina, so it is a perfect pozzolanic material. It can be used as supplementary cementitious material and it can be used as a source material in the production of geopolymer concrete. The next one will be GGBS. GGBS is also called as ground granulated blast furnace slag because it is produced from the blast furnaces. It is given the name as GGBS. It is a byproduct from the blast furnaces used to make iron. So these operate at a temperature of about 1500 degrees Celsius. In the blast furnaces, the temperature is around 1500 degrees Celsius will be maintained. So here the coke, iron ore and limestone will be fed inside this blast furnace and it is subjected to high amount of temperature. Then this iron ore is reduced to iron and the remaining materials form a slag. If you look at here, the molten slag will be formed. That slag will be periodically tapped off as molten liquid and it should be rapidly quenched in large volumes of water. Then it is grinded using the grinding mill and we will get the ground granulated blast furnace slag. And in between also in the form of slag it will be taken out, which is coarser in size, can be used as slag sand as partial replacement to sand. But here in the preparation of geopolymer concrete, it should be used as a precursor or source material. So ground granulated blast furnace slag will be used. It is rich in calcium oxide, silica and alumina. Next one is silica fume. Silica fume, it is a byproduct from the silicon or ferrosilicon industries. Here the quartz is heated by wood chips and coal in an electric furnace. Okay, at a high temperature of 2000 degrees Celsius to reduce oxygen content in silica oxide. Then this fume condenses and oxidizes at the top of furnace to form silica oxide. So it is silica fume, how it is generated, because it is subjected to huge amount of temperature and it will be grinded to the fine powdered form. So it is the particle size will be very, very small compared to all the other pozzolanic materials. It is very rich in silica. Silica content of the silica fume will be very high. And the next one will be agro-based material. This is rice husk ash from the rice plant. When the separation of rice husk and rice will be taken, this rice husk, first it should be washed thoroughly. Then the dry rice husk should be kept in an oven at a temperature of 150 degrees Celsius. So it will be dried and this rice husk will be burned at a temperature of 600 to 800 degrees Celsius. Then the ash will be cooled and again grinded to get the fine powdered form of this ash, which is called as rice husk ash. So it is also rich in silica content and the fineness also will be very high. And then the next agro-based material is sugarcane bagasse ash. In the recent years, much amount of research is being progressed in this particular area. After identifying the silica rich or the silica content, alumina content in this particular bagasse ash, much amount of research is being conducted in this particular area. So from the sugarcane industries, when the bagasse is produced, that bagasse will be like burned to get a fine powdered form. So that will be called as sugarcane bagasse ash. It is given rich silica and alumina content, so it can be used as source material in the production of geopolymer concrete. Then comes to the marble dust. In the production of marble dust, marble industry, this marble dust is produced as a byproduct during the marble processing stage, cutting stage, polishing stage, and cutting slab into desired pieces. In all the stages, this marble will be formed in the form of this small powdered form. This powdered form, if we just check this powder can represent around 25% of the original marble block. So that much amount of wastage is produced from the marble industries. So this marble dust is a rich source of calcium oxide, so it can be used as admixture to geopolymer concrete. Then the red mud. So this red mud is a waste product created during the extraction of alumina from bauxite. In the bauxite industries, from the Bayes process, this red mud is produced. It is also rich in alumina and silica, so it can be used as source material. Then the next one will be the palm oil fuel ash. It is also agro-based material. So here, this palm oil from palm oil fuel ash is generated by the combustion of agricultural residues like palm fibers and palm kernel shells in biomass thermal power stations. From that, we'll get this palm oil fuel ash. So it is also rich in silica and alumina, so it has a potentiality to make use as source material in the production of geopolymer concrete. Then ceramic waste powder. From the ceramic industries, when the ceramic waste is collected, crushed into small pieces, then grinded to get the fine powdered form, ceramic powder we will get. Again, this is rich in silica and alumina, and in between it is sieved to get the desired size. It is rich in silica and alumina, so it can be used as best source material in the production of geopolymer concrete. Waste glass powder. So the waste glass powder production process typically involves collecting the waste glasses, sorting it to remove the contaminants, crushing it into the small pieces, then washing to further clean it, and finally grind it and sieve it to get the glass powdered form. So it is rich in silica and alumina, so it can be added as a source material in the production of geopolymer concrete. Then the paper sludge ash. It is best it can be used as it is a best source of calcium oxide. Rich calcium oxide will be there from the paper sludge. So in the paper industries, when the raw paper sludge collected from the sludge tank, then the sludge is dewatered and sun-dried for 5 to 6 hours. Then it is incinerated in the muffle furnace for 2 hours at various temperatures, at different temperatures, and further it will be sieved to get the paper sludge. So it is again rich in calcium, silica, and alumina. So it also can be used as a source material and also can be used as a admixture to the geopolymer concrete. Then the next one will be the sewage sludge ash. Sewage sludge ash is a waste material created when dewatered sewage sludge is burned in an incinerator. This also rich in silica and alumina. So recently in our college, this sewage sludge ash is collected from in Hyderabad. One waste to energy plant is created in Jawahar Nagar by JHMC. So the outcome, that is waste product from that, is incinerated bottom ash. That bottom ash was collected, and when XRF and XRD studies were conducted on that incinerated bottom ash, it is identified that it is rich in silica and alumina. So this sewage sludge ash also can be used if at all the contaminants are controlled, then it can be used perfectly as a source material in the production of geopolymer concrete. Then the wollastonate. When the natural materials, natural ore, when the limestone and the dolomite undergoes high temperature and pressure condition, then it often, in the presence of silica-bearing material, then it lead towards a metamorphic process and it will be converted to calcium carbonates, and that will be grinded into the fine powder to get this wollastonate. It is also a rich source of calcium oxide. So like this, if we just see the list of all the materials are either rich in silica alumina or rich in calcium oxide along with certain amount of silica and alumina. So these materials can be used individually to prepare geopolymer concrete or in suitable combinations to get a sustainable geopolymer concrete. So there is a possibility of conducting the research in the geopolymer concrete with the help of these alternative materials. With this introduction to geopolymer chemistry and source materials, now I am going to discuss about one research conducted in our college. Before that, the breakdown of geopolymerization process, we quickly just look at, that is metakaolin based geopolymerization. Just now I discussed about the dissolution of the material, polymerization, gel formation, hardening, how it is going to occur. So we need to understand first the dissolution of the metakaolin and alkaline medium do occur. Then immediately polymerization, oligomerization, polymerization and gel formation will occur. Then hardening process. When it is hardened, it will give a geopolymer matrix, as said in the form of NaSH. It is common for metakaolin, fly ash, rice ash or volcanic ash, sugarcane bagasse, because all are rich in silica and alumina. When it comes to GGBS, because ground granulated blast furnace slag is having high amount of calcium oxide, silica and alumina is also there. So there will be slight change in the geopolymerization process or chemistry in the geopolymerization process. So what are the reactions involved? First, dissolution of slag compound. I said here that it is rich in calcium and silica also. So calcium and silica, they will be dissolved. And they will be converted into this particular form, hydroxide, silica hydroxide. Then comes to the polymerization. In the polymerization, in the earlier stage, it is giving NaS, sodium aluminate silicate hydrate gel. But here it is rich in calcium, it is going to give calcium silicate hydrate first. Then again that calcium silicate hydrate is going to form into calcium aluminate silicate hydrate because it is equally rich in aluminate. So it is going to form a product called as calcium aluminate silicate hydrate. The very important aspect of this slag-based geopolymerization process is the setting of geopolymer concrete. When the GGBS is added, it sets very fast compared with respect to fly ash geopolymers. So if you look at the literature in the geopolymer concrete, most of the geopolymer concrete produced by using fly ash is done by the Curtin University. A professor named Rangan BV. He conducted several experiments on fly ash based geopolymer concrete because fly ash reaction rate is less. So the geopolymer concrete was prepared using the heat curing conditions. Heat curing is maintained up to 60 to 80 degrees temperature up to for 1 day. So the geopolymerization process was occurred and they got NaSH. But in case of practical considerations, every time the concrete need to be prepared using the heat curing conditions is not possible. So that is the reason calcium oxide rich material like GGBS was introduced as a admixture to the fly ash based geopolymer concrete. So thereby it is giving calcium aluminate silicate hydrate gel. The setting action of this geopolymerization process is very fast compared with respect to fly ash geopolymers. When only the fly ash based geopolymers tried to prepare, it was taken around more than 2 days time to set. when it comes to GGBS, when the GGBS is added in different proportions, then the setting time was rapidly increased, like from 2 days to 1 day, then again 60 minutes, then again 45 minutes, like that it was reduced. So that is the reason GGBS can be taken as a better material in the geopolymer concrete as an admixture to fly ash based geopolymer concrete. As I mentioned just now, in case of wollastonite, in case of making use of the materials like marble dust, etc., which are rich in and the paper sludge, etc., which are rich in calcium, can also be used. GGBS is used nowadays. Much amount of research. If you click on the net, like geopolymer concrete, you will get much amount of research in the combination of fly ash and GGBS, but you will not find with other alternative materials. So there is a scope for research to conduct in using that combination of the other alternative materials which I listed. Then the next one will be the alkaline activators. First, we considered, or we understood about the source material. What are the different source materials used in the preparation of geopolymer concrete? Then comes to alkaline activators. In the case of alkaline activators also, sodium hydroxide and sodium silicate combination of materials are used widely. Our potassium hydroxide and potassium carbonate materials are used. Potassium silicate was used widely to get the geopolymer product. But along with this, some more materials are there which are rich in alkaline medium, alkali content, which are called, I have given the list here as sodium carbonate and sodium aluminate, magnesia. So that materials also can be added, because sodium hydroxide cost is very high compared with respect to the other materials. At the same time, toxic nature of sodium hydroxide will be very high. So because of that reason, much care need to be taken to prepare alkaline activators, and it is not environmental friendly. So that is the reason now the research is progressing towards identifying the alternative alkaline activators. So now the research is open to conduct using the sodium carbonate based alkaline activators, or sodium aluminate based alkaline activators, or magnesia, like that. It can be conducted. So this is about the alkaline activators. Then after discussing about source materials, what are the different possibilities of using the source materials, then the next one is alkaline activators. Then we'll move towards we will move towards one case study, which is, I said, this experimental study is conducted in our college. It is strength and durability properties of fly ash and GGBS based geopolymer concrete. So here, this research work is a comprehensive investigation to arrive at the mixed proportioning and performance of GPC, both in terms of mechanical and durability properties. Because if you look at, there is no Indian Standard Code or any other code specifying about the mixed design, how mixed design should be conducted for the geopolymer concrete. At the same time, we cannot even make use of IS 10262 because the materials used in the geopolymer concrete are completely different. At the same time, it is going to depend on several aspects. That is the reason the first objective of this case study is to arrive at the mixed proportioning and to give the grading to the geopolymer concrete. Then after giving the grading to the geopolymer concrete, the next step will be identifying the mechanical properties and also durability properties of this proposed geopolymer concrete. In this particular work, the materials used are, the precursors will be fly ash and GGBS based precursors are there. Alkaline liquid will be a combination of sodium hydroxide and sodium silicate. Because compared with respect to potassium based alkaline activators, sodium based alkali activators are more reactive in nature. So that is the reason sodium based material only used in this particular work. And the studies conducted, I said parametric study is conducted to achieve grading of geopolymer concrete. Then the strength properties and durability properties are conducted. And then to begin with, the mixture proportions of geopolymer concrete is done using the guidelines given by Ranga. And when the literature is searched to get to see what are the different parameters influencing the strength of geopolymer concrete, then it is identified that here source material is going to influence the strength of geopolymer concrete. Then the aggregate content, if the aggregate content varies, then strength of geopolymer concrete is going to differ. Then alkaline liquid to source material ratio, that ratio also is going to influence the strength of geopolymer concrete. Then the type of alkaline activator, that is a sodium silicate and sodium hydroxide, the ratio between them also is going to influence the geopolymer concrete strength. Then the molarity, because concentration of sodium hydroxide play a very important role in geopolymer concrete. So if the concentration is decided based on the molarity, so the molarity also playing an important role. Then the type of curing, I said heat curing was used by different researchers. So heat curing or ambient curing based on that. So these are the 6 parameters considered to get the optimum mixture proportions of geopolymer concrete. Then after getting the optimum mixture proportions, then the strength properties are identified, like compressive strength, flexural strength, split tensile strength, Young's modulus, and Poisson's ratio as per the standards. Then the durability of concrete. So durability of concrete is actually depending upon the different causes like physical cause, mechanical cause, chemical cause. Under the physical causes, freezing and thawing action, penetration properties, thermal expansion, all are going to influence the durability properties of concrete. Then under the mechanical causes, impact, abrasion, erosion, these properties are going to influence the durability. Then the chemical. In the chemical causes also, internal chemical cause will be there, external chemical cause will be there. Internal chemical cause like alkali aggregate reaction, alkali carbonate reaction, all these reactions will be there, which are going to cause in the internal core of concrete. Then the external chemical cause, chemical exposures. So external exposure, whenever the concrete is submerged or like inserted in under like different mediums, let us say acid exposure, sulfate exposure, etc., how it is going to influence or how it is going to change the properties of concrete. So this is what is considered. So here in this particular study, all the penetration properties are identified. Then in the mechanical, under the mechanical cause, abrasion test is conducted on the geopolymer concrete. Then alkali aggregate reaction test is conducted. Then the chemical exposure, like sodium, sulfate, acid, and chloride exposures are conducted on the proposed geopolymer concrete. The materials used here are fly ash, GGBS, then sodium hydroxide and sodium silicate solution. Then first stage will be the parametric studies. Parametric studies, the importance of these parametric studies is to identify the optimum mixture proportions to give grading to the geopolymer concrete. First, as the code is not there to conduct mixed design of geopolymer concrete, first the mixture proportions of geopolymer concrete were considered based on the guidelines given by Rangan. But these mixture proportions, whatever are considered by Rangan, are not yielding the desired strength. This problem maybe all the researchers might have faced, because the guidelines given by Rangan are based on their climatic conditions, material proportions, etc. In India, if you want to try, most of the results are not matching. So as there are no standard guidelines available on proportioning of geopolymer concrete mixtures, parametric studies have been planned as part of the first phase of this particular work. So here these influencing parameter considered are the percentage of total aggregate is considered, molarity of NaOH is considered, and alkaline liquid to fly ash ratio, percentage of GGBS replacing fly ash. Then the curing conditions, ambient and curing conditions are considered. Because it is the parametric variation, this parametric variation is done in different stages. First stage, the total aggregate proportion in concrete, it actually varies. Normally, it varies in between 70 to 80%. Here to start with, first it is made as constant. Total aggregate proportion is taken as 70%. Then, as per the literature, it is identified that as the molarity of NaOH is increasing, geopolymer concrete strength is increasing. And most of the researchers, they have done the research in between the molarity in between 8 to 16. So that is the reason in this particular work also, the molarity of NaOH is considered as 8, 12, 16. So 3 variations are taken. Then comes to alkaline liquid to binder ratio. So here alkaline liquid to binder here is fly ash and GGBS. So that ratio is considered as 0.3, 0.5, 0.7. Now you will be surprised why at all 0.7 alkaline liquid to binder ratio is considered. Because when the research is look back, then it is given that the guidelines given by the Rangan or other researchers, they have tried using this alkaline liquid to fly ash ratio in between 0.3 to 0.5. Or some of the researchers even tried with 0.65. 0.6, or some of the researchers, they went up to 0.65 also. So that is the reason in this particular work, 3 different variations of alkaline liquid to fly ash ratios are considered as 0.3, 0.5, 0.7. Then comes to GGBS variation. As it is mentioned already, fly ash will take so a longer time to set to have a geopolymerization product. And to enhance that setting action, to shorten the setting time, GGBase is added because it is rich in calcium. So that calcium oxide, the GGBase is added. The percentage replacement of GGBS considered here is 10 to 50 percentage, 10, 20, 30, 40, 50 percentages. So this variation is also considered in the stage 1 parametric variation. Up to after 50% is also considered in the trial mix. Then it is identified that when the GGBase dosage is increased beyond 50%, its setting time is shortened below 30 minutes. So its setting is too fast. And under the practical conditions, we know that at least 30 minutes time should be there to set. So that is the reason the amount of GGBS is curtailed up to 50%. And to start with, the first ambient curing conditions are only considered in the stage 1. And that stage 1 results are if at all, if you just see the stage 1 results, they are shown here for different molarities of NaOH. This is the one set of results. And for alkaline liquid to fly ash ratio of 0.3, and alkaline liquid to fly ash ratio of 0.5, alkaline liquid to fly ash ratio of 0.7 for different GGBS dosages, right? So first, if you just check with respect to the molarity, as the molarity increases, compressive strength increases. But in combination with GGBS, if the molarity improvement is seen, it is showing only a little improvement in the compressive strength, that too only 4 to 6%. Almost the similar kind of result is being observed in all the cases. So that is the reason here. And keeping in view the cost of sodium hydroxide and toxicity nature of sodium hydroxide, for the next stage of work, molarity of NaOH is maintained constant as 8. The next variation is alkaline liquid to fly ash ratio. If you look at alkaline liquid to fly ash ratio 0.3, 0.5, 0.7, almost similar kind of result is being observed. But when we just check how the mix is prepared, mixture of alkaline liquid to fly ash ratio of 0.3, it was very stiff. Getting the mix itself is stiff because fly ash, this alkaline liquid is very less with 0.3 ratio. Because it is very less, this mix requires a huge amount of superplasticizer. Superplasticizer is added up to 10%. Okay, so which is undesirable, especially for 16 molarity mix. It consumes more amount of superplasticizer. It is not desirable. That is the reason this 0.3 mix was not used for the further works or further stages. And when we check with the alkaline liquid to fly ash ratio of 0.7 mix, this mix is consisting of more amount of alkaline liquid compared with respect to these 3. It is consisting of more amount of alkaline liquid. If we see the nature of alkaline liquid, it will be too cohesive, right? So when the too cohesive liquid is there in the mix was having a better workability, but it is very difficult to handle the mix because of this higher amount of alkaline liquid. So that is keeping that in view. This alkaline liquid to fly ash ratio was not considered as 0.7. So now comes to the alkaline liquid to fly ash ratio mix of 0.5, which is giving the moderate workabilities, and it is not consuming much amount of superfly laser also. So that is the reason from this stage 1 results, it is maintained. Molarity of NaOH is maintained as 8. Alkaline liquid to fly ash ratio is maintained as 0.5. At the same time, if you just check in each set, as the GGBS dosage is increasing, let us say 10 to 50%, almost the compressive strength increment is observed by 150%. So that much tremendous increase in the compressive strength is observed with the addition of the GGBS. Why? Because it is going to give, along with sodium aluminate silicate hydrate gel, it is also giving calcium silicate aluminate hydrate gel. So that is the reason it is giving huge amount of compressive strength. Keeping that in view, for the next stage of investigation, GGBS dosage is maintained as variation only because it is giving improvement in the strength. Then in the first stage, total aggregate content was maintained constant at 70%. Now we want to check the variation. What will be the influence of variation of total aggregate on the compressive strength? So it is now taken the variation as 70, 74 and 78%. Again, the ambient curing conditions are only considered in the geopolymer concrete. So next stage of investigations, they are revealing that as the total aggregate proportion is increasing from 70 to 78, the compressive strength increment is up to around 3 to 4%. 3 to 4%. Okay, for different GGBS combinations, it is not giving much. It is not showing much influence on the compressive strength. So that is the reason again for the next stage of work, 70% of total aggregate is only maintained, because when we just check with respect to 70% and 78%, 78% of the mix will be consisting of only 24% of alkaline liquid and fly ash. Okay, that is a binder content. So we want to, like in the geopolymerization process, the binder play a very important role. So that is the reason to promote or to improve the binder content, 70% of aggregate content only maintained for the next stage of work. That is the third stage. So in the third stage, 70% of total aggregate is maintained. From the second stage, molarity and alkaline liquid to fly ash ratios are already maintained constant. Then the GGBS anyways, percentage GGBS is improving the compressive strength. So that is the reason, that is again the same variation is considered. Then comes to the curing, because in the earlier stages, ambient curing is only considered, the effect of curing is not considered. So here, both the type of curing conditions are considered, that is heat curing and ambient curing. In the heat curing, the curing of the samples is done in the oven up to 60 degrees temperature for 1 day. That samples were again crushed for compressive strength, and ambient curing were conducted, and the results were shown like this. If we just check here, this red color like line indicates towards the heat curing. As the heat curing, okay, ambient curing and heat curing, as the heat curing is done on the geopolymer concrete specimens, it is showing improvement in the compressive strength. Around 10 to 15% improvement of compressive strength is observed. But at the same time, it is seen that when the GGBS dosage is increased, the difference between the ambient curing and heat curing is reduced. So almost the same same amount of compressive strength is observed in between the ambient curing samples and heat curing samples. The reason may be because of the resulting hydration due to increased calcium content, because the GGBS addition is more, calcium content is more, due to that hydration process is evolving. So in the ambient curing also, because of that hydration process, it is giving good improvement in the compressive strength. So as in the higher grades of higher dosages of GGBS, there is a very little difference between the heat curing and ambient curing samples. And keeping in view practicality, ambient curing only considered for the next stage of work. So in the fourth stage, we got total aggregate content as 70%, molarity 8, alkaline liquid to fly ash ratio as 0.5. Then ambient curing conditions are considered, then the variation of GGBS, because it is seen that from 10 to 50% improvement, it has shown a good improvement in the compressive strength. That is the reason now only GGBS dosage, how it is going to improve the compressive strength, it is seen by decreasing the interval to 5. That is 5%, 10%, 15, 20, 25 like that. And based on this, it is observed that the percentage replacement of fly ash with GGBS is increased from 5 to 50%. Then the compressive strength increased from around 30 MPa to 70 MPa. So based on this, as this 30 MPa is meeting the target strength of 38 MPa is meeting the target strength of around let us say M20 grade concrete, and this the last one, it is meeting around 60 M60 grade concrete. So based on this, the optimum mixture proportions are arrived in such a way that the compressive strength of all GPC mixtures under investigations are attained the target strengths which are specified for up to from M20 to M60 grades. That is the reason here to differentiate between the normal conventional grade concrete and geopolymer mix. The designation given here as GM20, GM30. G stands for geopolymer and M stands for mixture. Geopolymer mixture of 20 MPa strength is specified as GM20. So for all the mixture proportions, the optimum proportions are identified. This will be the first stage of work. Then in the second stage, all the mechanical properties are identified, like compressive strength, flexural, tensile strength. All the mechanical properties of this geopolymer concrete are meeting to the level of normal concrete, conventional concrete of the same grade, M20 to M60. So this is about all the like modulus of elasticity, theoretical modulus of elasticity, which is done as per the Indian standards IS 456. It is compared with respect to experimental modulus, and the like percentage error will be within 15%. So it is giving a good what is called as a comparison. It is meeting up to the level of conventional concrete. All the proposed grades of geopolymer concretes are showing the same level of mechanical properties as that of the conventional grade. This is about the mechanical properties. Immediately after the mechanical properties, these mixtures were taken for scanned electron microscopic observation. So next, SEM pictures, scanned electron microscopic pictures. This using this scanned electron microscope, the study was conducted on this geopolymer mixture, proposed grades of geopolymer mixtures. At the same time, the chemical analysis was done using EDAX pics, which is shown. First one is fly ash based geopolymer concrete. To see how the geopolymerization process is varied in terms of microscopic observation, first we tried with fly ash based geopolymer concrete. That means only fly ash is used in the production of geopolymer concrete. In that, if at all, if we just check, it is 28 days sample, 28 days cured sample is taken. So in this, if this is reacted fly ash, this fly ash cenospherical shape is depicting the fly ash. On the top of that, geopolymer product is there, and these are non-reacted fly ash. So here it is clearly seen through the SEM pics on the fly ash based geopolymer concrete that little amount of this reactive products are observed on the fly ash. More amount of this non-reacted fly ash are seen. That means after 28 days, much amount of fly ash is available, which is non-reactive, because of like when we just like discussed about fly ash based geopolymer concrete, then there we understood that fly ash based geopolymer concrete take much amount of time to have a reaction, slow setting, etc. The reason is identified, or again let us say it is validated through SEM pics. 28 days fly ash based geopolymer concrete, where more number of fly ash particles are seen without reaction products. And this is sodium aluminate silicate hydrate gel, which is confirmed through EDAX pics. Because in the EDAX pics, chemical composition percentage weights are taken into consideration, where silica by alumina ratio is considered, which is coming in between 1.5 to 2, confirming the presence of NaSH gel. Then comes to the proposed grades. Then the proposed grades like GM20 and GM30, these grades are considered. Then these grades are having a GGBS dosages, right? As the GGBS dosage is increasing, we can see clearly the traces of GGBS, calcium, and CaSH gel. Along with the sodium aluminate silicate hydrate gel, calcium aluminate silicate hydrate gel is also seen. This is confirmed through calcium by silicate ratio. So we can here it is we can just see here in case of GM40 also more traces of reactive fly ash is there. Again GGBS is there. Calcium aluminate silicate hydrate gel formations are there. And again this calcium aluminate silicate hydrate and sodium aluminate silicate hydrate presence can be witnessed through this EDAX pics. From the EDAX pics, the percentage weights are considered. All the percentage weights are plotted for different types of mixtures. The first one is a fly ash GPC, then GM20 to GM60. It is given. All since this GM20 to GM60 grades have silica by alumina ratio more than 1.65. Even when like GM60, if you look at it, is having highest amount of GGBS, still silica by alumina ratio is maintained as more than 1.65. More than 1.65 means it is confirming the presence of geopolymer product, that is sodium aluminate silicate hydrate gel. And along with that, some traces of calcium aluminate silicate hydrate gel is also confirmed through calcium by silicate ratio. When we just take the ratio between calcium by silicate, it is ranging from 0.97 to 1.7. It is confirming calcium aluminate silicate hydrate. Increasing the calcium content through the addition of GGBS, it is causing a more compact and finer microstructure. If you just look at here, more compact and finer microstructure is observed because the calcium is acting as a seeding or precipitating element. So from this, it is clearly seen that the addition of GGBS is improving the microstructure. It is making the microstructure of geopolymer concrete compact. At the same time, it is improving the setting action. So the compressive strength of geopolymer concrete is increased with the addition of GGBS. Then durability properties are identified. These are the durability properties which are identified like water absorption test, sorptivity test, permeability in the penetration characteristics. Then the chemical resistance, sulfate resistance test, acid resistance test, and RCPT, rapid chloride penetration test is conducted, and the respective codes are specified here. Alkali silica reaction test is conducted as per the two codes. One is as per the Indian standard, that is motor bar test. ASTM standard, that is accelerated motor bar test. Abrasion test, which is underwater method, which is conducted as per the ASTM standards. Then comes to the durability results, water absorption results. Overall, the results of this water absorption, if you look at in the geopolymer concrete of 20 grade and the conventional concrete of 20 grade are showing little difference between the water absorption capacities. But as the GGBS is increased, that means higher grades of geopolymer concrete, GM60, almost similar water absorption characteristics it is having because of improvement in the this compact crystalline nature with the addition of GGBS. Overall, if you look at the overall water absorption is less than 5%. So we can conclude that it is having the low water absorption, which is according to Vic Road's standard specifications. Then the sorptivity test. Sorptivity test is conducted as per the ASTM standards. Here the initial sorption is conducted. Initial sorption conducted for first 6 hours. Then the final sorption. Final sorption and initial sorption intersection is considered. Final sorption as per the code, it should be conducted up to 7 days, the sorptivity test. So then the final sorption value you will get. Then the theoretical sorption, the equation specified by the code to get the sorptivity, based on that sorptivity value will be achieved. So here it is mentioned that sorptivity index of geopolymer concrete is less than 0.2 mm per square minute. It is considered to be acceptable quality in terms of water tightness. As per the earlier literature, it is specified that if the sorptivity index is less than 0.2 per square minute, if you look at it, is less than 0.2 only. So it is having the highest acceptable limit in terms of water tightness. So the proposed geopolymer concrete have water tightness nature. Then the coefficient of permeability. So permeability test is conducted on the geopolymer concrete and the conventional concrete of the same grades. It is seen that as the grade increases, coefficient of permeability of both, it is almost same. It is depicting the same as that of the water absorption characteristics. So out of this, we can say that penetration characteristics of geopolymer concrete and conventional concrete are almost same. It is behaving in a similar way. Then chemical exposure. Chemical exposure here, first is sulfate exposure results. Visual observation is seen here in the sulfate exposure. Two types of chemicals are used: sodium sulfate, magnesium sulfate. This specimens which are immersed in magnesium sulfate are seen here. Excuse me. It is observed that the impact of magnesium sulfate solution on strength on the specimens is high compared to the sodium sulfate solution. So it is witnessed, if you look at this GM60 samples, the surface is almost covered with the white patches after 56 days of exposure. These samples are taken after 56 days of exposure with the little surface degradation. Surface degradation is not seen clearly. But when we see ordinary Portland cement concrete, significant white patches formation along with the surface degradation is seen on this conventional concrete. So geopolymer concrete is showing the superior behavior compared with respect to the conventional concrete when exposed to the magnesium sulfate. Then the change in weight is considered, then the loss in strength is also considered. In the loss in strength, if it is observed, loss in strength is increased with increase in grade of concrete. Surprisingly, it is seen that as the grade of concrete increases, the loss in strength is increased because it is exposed to sodium sulfate and magnesium sulfate also. It can be seen. The probable reason for this behavior may be attributed to the higher calcium content reaction with sulfates, because GGBS dosage is increased, which is having calcium content. So that calcium content is reacting with the sulfates, and degradation of material is occurring. Because of that, loss in strength is increased. But when we just look at the conventional concrete, the percentage loss in strength is as high as 32 to 39%, whereas when you just look at it is 13% and around 18%, which is various. So still, even though calcium is added, additional calcium in the form of GGBs is added in the geopolymer concrete, even though the calcium is reacting with sulfates, its resistance against the sulfate will be very high compared with respect to the conventional concrete. That is what we can conclude through this particular study. The next one will be the sulfate exposure test. Along with this what is called as the this percentage loss in strength and loss in weight loss, strength loss, sulfate expansion test is also conducted using the motor bars. Then the result depicts the similar kind of behavior. If you look at OPC motor bar is showing much amount of white patches. Normally, whenever sulfate is attacking on the concrete, the physical observation will be through formation of white patches. White patch is nothing but Ettringite, right? Ettringite formation is very high compared with respect to geopolymer products. Percentage elongation is also percentage elongation increasing from 0.031 to 0.15%. In case of maximum amount of increase is seen in the when the samples are immersed in magnesium sulfate. But when it compared with respect to the ordinary Portland cement based mortar, where higher amount of expansions are seen, 0.28% and 0.41%. So it is again we can say that better resistance capability of proposed geopolymer concrete compared in the sulfate solution compared with reference to the ordinary Portland cement mortar bars. SEM picks also the same geopolymer concrete specimens, again immersed in sulfate solution. The SEM picks are taken out. SEM picks are also confirming the presence of Aggregate formations as seen in this pics. Okay. Next, the elemental ratios. Elemental ratios confirming the how the magnesium sulfate is influencing or how it is influencing the properties of the proposed geopolymer concrete. If we look at here, it is seen from the earlier slides that as GGBS is increased in the production of geopolymer concrete, calcium aluminate silicate hydrate gel is propagated in geopolymer, right? Then if we just look at the same kind of phenomenon, that means this calcium rich material are like reacting with what is called as geopolymer sulfates and influencing the calcium silicate hydrate gel, right? So that can be seen through this calcium by silicate ratio. If at all, if we just look at from the grades GM20 to GM60, the calcium by silicate ratio is increasing. But if we look at the calcium by silicate ratios for this what is called as conventional concrete, they are increased by an amount 26% and 30% respectively in sodium sulfate and magnesium sulfate solutions. So that is the reason we can say that all designated geopolymer concrete specimens show better resistance to sulfate compared to the normal concrete. Then the specimens are immersed in acid. Here two types of acids are considered, HCl, that is hydrochloride solution, and sulfuric acid. Then this GPC specimen, that is geopolymer concrete specimen, this is GM60, and this is conventional concrete. When they are exposed to this HCl solution, we can see that aggregate exposure is not happened in case of geopolymer concrete, whereas in case of the conventional concrete, we can see the aggregate exposure. Okay, when it is subjected to removal of mortar is happened and aggregate exposure is seen on the samples when it is exposed to HCl solution. In case of sulfuric acid, we know that the sulfuric acid solution impact will be more than HCl on the concrete specimens. So it is again immersed in 5% sulfuric acid solution, the specimens, geopolymer concrete specimens and conventional grades. Here, if we just look at GM60 specimen, is exposed to sulfuric acid, and it is suffered more compared with respect to GM20, initial grades of geopolymer concrete, compared with respect to this GM60. They are intact. And GM60, if we just look at, it is also intact. It is not showing any aggregate exposure. Normally, when we just take the literature, whenever the concrete is exposed to the acid, the basic phenomenon will be removal of mortar and aggregate exposure. Aggregate will be exposed, that to sulfuric acid. So here, if we just see a GM60 sample, nowhere little amount of surface degradation is occurred, but nowhere we can see removal of mortar and aggregate exposure. This specimen is after immersing this GM60 in H2SO4 solution for 180 days. But when it comes to the equivalent conventional concrete, that concrete, how it is affecting that sulfuric acid, how it is affecting the conventional concrete is seen through this pics when it is immersed in solution for 28 days and 56 days. After 56 days, more amount of degradation of sample is occurred, more softening of material. It is not possible even to handle that particular concrete. That is the reason after 56 days only that samples are taken out. After 180 days, the test is not conducted. So here with this only we can clearly say that geopolymer concrete, proposed grades of geopolymer concrete are showing a high or superior resistance against the sulfuric acid compared with respect to the conventional concrete. Because after 180 days also aggregate exposure is not seen, but when it comes to the conventional concrete, after 56 days only, the specimens are taken out from the solution. So it is seized after 56 days only. Same is confirmed through loss in weight and loss in compressive strength. As the grade of geopolymer concrete increases, loss in strength is increased, but it is increased up to 18% in case of HCl solution immersion and up to some 28% in case of sulfuric acid solution, that too after 180 days. But conventional concrete, when it is immersed in HCl solution, it is showing 50% reduction in the compressive strength. And after 56 days only, 79% reduction in the compressive strength is occurred. So it is again confirming the superior behavior. The same is seen through the SCM picks. GM60, if we just see decomposition of geopolymer product is seen through this on the top of fly ash particles. If we just look at the decomposition of this geopolymer product is visualized. At the same time, some parts it can be seen formation of Aggregate and formation of gypsum. And in case of normal concrete, conventional concrete, the complete decomposition of calcium silicate hydrate is seen through the sulfate concentrations. The same is being depicted again through the atomic percentage weight of the samples. As the grade of geopolymer concrete increases, sulfur content is also increased. That means the effect of this sulfuric acid is more on the GM60 samples than GM20 samples. So this is about acid exposure. So after the acid exposure, then again RCPT results, that is rapid flow rate penetration test, is conducted on geopolymer concrete, proposed grades of geopolymer concrete. Here, if you just look at GM20 sample is having only 10% of fly ash. Because it is having only 10% of fly ash, that is the reason its reaction rate will be very slow. And now after 20 days, it will not get it full strength. So keeping that in view, the samples, 28 days samples and 90 days samples, both the samples are taken out for RCPT test, and the test is conducted. So here, from this results, it can be observed that chloride permeability decreases as the curing age and the grade of GPC is increases. If you see grade of GPC and in between this 20 days and 90 days, if we just look at as the age increases, curing age increases, the chloride permeation is decreased, and the grade increases, chloride permeation is also decreases. When it compared with respect to the normal concrete, similar kind of behavior is observed in between the geopolymer concrete and normal concretes. Based on ASTM standards, that is ASTM-C 1202 code guidelines, this chloride ion permeability of this GM20 and GM30 is classified as low permeation. 40, 50 and 60 grades of geopolymer concrete are classified as very low. Whereas in case of normal concrete, M20 and M30 grades are classified as moderate, 40, 50 are classified as low, and 60 is classified as very low. So almost similar kind of behavior is observed in case of chloride ion permeation rate. The next kind of test is conducted, which is alkali silica reaction. The main aim behind conducting this alkali silica reaction is whenever the geopolymer concrete need to be prepared using the locally available material which are rich in silica content. Thereby, it may promote the alkali silica reaction in the geopolymer concrete. How much amount of resistance it will give, in terms of alkali silica reaction, to check that this test is conducted. First, motor bar test is conducted as per the Indian standards. To check the alkali silica reaction, the type of aggregate considered here is quartzite. Quartzite type of aggregate which has reactive silica, that aggregate is added in the preparation of geopolymer mortar. Again here, to prepare geopolymer mortar, 10% of GGBs is added to a 90% of fly ash, and up to 50% of GGBS and 50% of fly ash. So same kind of compositions are considered even to prepare the mortar bars. And percentage elongations are calculated after 12 months. That means this test is conducted up to 1 year. As per the IS 2386 Part 7 code, it is mentioned that if at all 6 months elongation is within 0.06%, then it can be stated as this material is not reactive. Even though if it is added with reactive aggregates, alkali silica reaction will not occur. So no, potentially it is proved to be deleterious. It is called as deleterious as per the standard. And as per ASTM standards, 12 months elongations, it should be within 0.04%. If you just check here in the all the grades of geopolymer concrete, up to 6 months, the percentage variation is percentage elongations are within 0.06, and at the same time 12 months it is below 0.04. So we can clearly state that the type of geopolymer mortar prepared, geopolymer concrete prepared are the using this reactive aggregate, still it is intact, still the alkali silica reaction is not occurring. Whereas in case of ordinary Portland cement based mortar samples, they failed. That means after 6 months its elongation is more than 0.06, and after 12 months the elongation is more than 0.04. So obviously clearly it can be stated that it is the ordinary Portland cement concrete cannot be prepared using this quartzite based aggregate, that is reactive aggregates. The same is being confirmed here through the microscopic pics. If at all, if it is observed geopolymer concrete samples, in this alkali silica reactive product is not seen. In this SCM pics, alkali silica reactive product is visible in the form of bright gel, like this. Bright gel. So bright gel is seen, alkali silica reaction gel, in case of ordinary Portland cement based mortar bars. And at the same time, crack propagation is also clearly visualized. And in case of this chemical compositions, this traces of higher traces of silica, sodium, that is accumulation of potassium, aluminum, sodium silicate, it is confirming the presence of alkali silica reaction expansive gel. So this is about the alkali silica reaction. Then the last test conducted is abrasion resistance test. It is actually underwater method to simulate the field conditions, especially whenever in the water, in the hydraulic structures, that small silt and some particles, whenever they are attacking on the concrete surface, then the abrasion do occur. To simulate that conditions, here this particular test is conducted as per the ASTM standards. As per this particular test, it is again clearly seen that as the grade of geopolymer concrete is increased, the abrasion average depth of abrasion is decreased. The same kind of phenomenon it is seen as that of the conventional concrete. It can be clearly seen through these pics. When these pics are subjected to abrasion, this is the M20 sample. When it is conducted for the abrasion test, we can see clearly the aggregate exposure because of the this depth of wear clearly seen, so that aggregate is exposed. And in case of M60 sample, some slight aggregate components are visible. When it comes to GM20, it is shown a superior behavior compared with respect to the conventional concrete, because it is not showing the after the abrasion test, it is not showing any trace of aggregate, and still intact behavior is seen with respect to this GM60. So it is showing geopolymer concrete specimens are showing superior behavior with respect to abrasion characteristics. And again, in between this GM20 and GM60 is showing still more superior behavior compared with respect to GM20 because of high strength. Then the conclusions, we can say that all the proposed grades of geopolymer concrete performance in terms of strength and durability is superior to that of the conventional concrete of same grades. So hence geopolymer concrete has potentiality to replace conventional concrete in near future. One more case study I thought of explaining. I'll just quickly show you that, because it is this research paper is still under review. I cannot tell you all the results. I cannot discuss here. In this particular work, we tried to prepare one cement, that is alkali activated cement. In the earlier work, the concrete is prepared. Here, the cement is prepared. That is dry powdered form of alkali activated cement is prepared. The source material used here are fly ash and GGBS. To prepare the alkali activated cement, alkaline activators are varied, like sodium hydroxide, magnesium oxide, sodium carbonate, sodium silicate. Different combinations, the materials were taken. Like this. This is the complete work. As this cement need to be prepared, these materials are mixed in dry form and they are grinded to the fine powdered form. For the grinding process, steel ball milling is used at NCCBM. So this particular work is conducted on different stages, stage 1 to stage 4, and the prepared geopolymer cement or alkali activated cement, on that different tests are conducted as per IS 4031. All these tests are conducted. After conducting this physical test, chemical test is conducted, like X-ray diffraction, XRD, XRF. Then the scanned electron microscopy pics are taken out and the evaluation is done. Then the particle size distribution is also done, that is granulometric investigation. All these investigations are conducted on this particular material. So major findings we got is all the properties of ordinary this geopolymer cement is similar to that of ordinary, but we got the grade up to 33 grade only. We didn't get 43. We got only up to 33 grade. As it is in the initial stage, we got 33 grade. So it has given encouragement towards progressing to get even geopolymer cement or alkali activated cement of 43 grade. Even in near future, we may get 53 grade geopolymer cement or alkali activated cement also. And then the last investigation, it is again taking different combinations of source materials by keeping this alkaline activator are constant. Like volcanic ash, this student is MN student. So in that particular country, fly ash is not available, volcanic ash is available. So we brought that particular material from that country, volcanic ash. And in different combinations, like combination with rhesus ash, silica fume, fly ash, GGBS is combined and the work is done. This is volcanic ash, and these are other source materials. And these are the properties of volcanic ash. If you look at the calcium oxide and silica, it is rich in silica. Calcium oxide is up to 10% only. It is having a alumina oxide of 15%. So like this, it is having the similar properties as that of the fly ash. So this is considered as the base material. That is, we are trying to get volcanic ash based geopolymer concrete with the all these additives like GGBS, fly ash, silica fume, rhesus ash. Out of this, we identified that GGBS, when it is added as partial replacement with volcanic ash, it is giving highest improvement in the strength. Then behind this will be the calcium content. Calcium content is improving the strength property of geopolymer concrete. Final conclusions of the study is the microstructure of optimum strength of geopolymer. Overall conclusions, I'll just tell you. Many more binder combinations can be tried as precursors to make geopolymer concrete more sustainable. As we discussed, fly ash and GGBS combination, like that, it can be tried with sugarcane bagasse combination, sugarcane bagasse and other calcium-rich material and other combinations, so that we can get geopolymer concrete which is cost-effective and also sustainable. Precursor combinations can be selected based on silica, alumina, and calcium contents in the materials to get improvement in strength and fast setting action. And the next one is alternative alkali activators can be tried to reduce toxic nature of alkali solution. I said sodium hydroxide solution, sodium hydroxide was used widely in the preparation of geopolymer concrete, but it is too toxic and it is very costly material. To get again economical and environmental friendly geopolymer concrete. Then we can try with other alkali activators. With the correct selection of the appropriate selection of material combinations, GPC can emerge, geopolymer concrete can emerge as a competitive alternative to traditional cement concrete, even in case of in situ concrete also. That means in the site prepared concrete also we can prepare or we can make use of geopolymer concrete on par with the traditional cement concrete. So these are the references. Thank you.
Thank you, ma'am. Thank you for your wonderful session. All participants, you have time for your question in the chat box. Please ask it as possible.
Somebody raised hand. Any doubt?
Yes, sir, you can put your query into the chat box.
Any specific filler material for reducing carbon dioxide emissions in concrete? Yeah, the materials which we discussed, like fly ash, GGBase, etc., all are reducing the carbon dioxide emissions. Okay, ordinary Portland cement, when we just see the production of ordinary Portland cement is evolving equal amount of carbon dioxide. Let us say 1 ton of ordinary Portland cement is prepared, then equal amount of carbon dioxide emissions will be there into the atmosphere. That is the reason all these supplementary cementitious material came in picture. So they are all like reducing the carbon dioxide emissions as partial replacement of cement in concrete. Okay, biochar also can be used, but here in case of biochar, some impurities will be there. Like I already stated, in case of like sewage sludge ash also, some impurities will be there. Like I said, we made use of this incinerated bottom ash, which is collected from this GHMC. There some amount of impurities were there. If that impurities were controlled, then that also can be used. So whatever the material you want to use as partial replacement to cement, it should be rich in silica and alumina. Also, even if it should be rich in calcium oxide. So that chemical composition should be considered before making use of any material in the preparation of concrete. That means chemistry of concrete, one should have a proper idea. So then you can make use of the materials. I'm going to share this PPT with the organizers. Anyways, ATAL program requires this PPT, right? Mohammed Jalaluddin.
Yes, ma'am.
Yeah, okay. I'll share this. No problem.
Yeah, ma'am. After the completion of session, you will get a presentation of whole 5 days session. Means total 13 sessions PPT into your WhatsApp and also into your professional mail IDs. Then before going to end the session, so I would like to thank all the participants for having the patience. We'll meet tomorrow by sharp 6 o'clock again, day 3.
Thank you very much.
Thank you, ma'am.
All the best to all the participants.